Hey, how's it going, Ghosts and Ghosts? Hi, happy Sunday. Oh my gosh, hello. Hi, welcome in, welcome in. I hope you guys are doing so good. Oh my gosh, it feels weird because I literally streamed like what? Thursday, Friday, and then Sunday, and then now here, yeah, like now Sunday, hello? I feel like I streamed like all week. Welcome in. How are you guys? I hope you guys had a lovely Saturday. I spent the majority of Saturday getting ready for this, and then I spent the majority of today getting ready for this. But how is everyone? Also, I'm very sorry that redeems are off. Last time I had a science stream, redeems were kind of going off a little crazy, so I was like, all right, well, maybe we should just turn them off for the stream because I have videos I want to show you guys, and I don't want to be like interrupting to those, especially because we have a quiz, a little fun little quiz at the end that you guys can potentially win a prize for. So I'm like, you probably want to pay attention so you can get all of the information so that you can do good on your quiz at the end. So it's gonna be fun. I'm really excited. So welcome in, Teague. Hi, Mads. Welcome in. Hi, Pizza. Welcome in. Hi, Cecil. Hi, Mama Spooky. Welcome in. Welcome in. Hi, Comedy. Hi, Josh. Hi, Emma. Welcome in. Oh my gosh, I am so ready. It's funny because I started making this and then I was like jumping all over the place with it. It was a big issue. Oh my god, that skill is so cool. Thank you. I'm glad you like him. He doesn't really have a name. It's just the freak. We call him the freak. That's about it. I also know that my tree's still up. I meant to take it down yesterday, but I got so busy that I didn't have time. So I'm gonna try to take him down after stream today. And then you won't see him tomorrow. I realized that like I have to put stuff back up. And I was like, ooh, I don't have time to be putting things down, putting things back up. And it's just like, we spent too much time getting ready for stream. It's fine. But welcome in, Finish, Flag Girl. If there's something else that you'd like for me to call you, please, by all means, correct me if I'm wrong. But thank you for popping in. I'm glad that you like the little skeleton. I took off his Santa hat. And I kind of wonder if I should have like given him a pair of goggles, like science goggles for his head, but I didn't think about it. And plus I did find a pair. I have a pair sitting around and I decided on these ones rather than wearing the safety glasses. 'Cause these ones, if you look at these bad boys, I used to wear these in the lab and these are the kind that go over another pair of glasses. And I was like, well, they're big boys. They won't cut off the circulation to my big old cranium. So it was like, you know what? It's fine. It's okay. Finn or Finish? Okay, is good with me. Okay, I'll remember that. Finn. I'm gonna ace this exam. I have my notes open. Hey, yo. Okay, also, just putting a disclosure, I may turn off my camera a few times because I didn't actually do my homework and see like where my camera was sitting on the presentation. So I don't want to be covering up any diagrams. So if there's anything like crucial that I want to talk about that's underneath something, I might turn off my cam for a little bit just so that you guys can see what I'm talking about so that I'm not moving my camera all over the place during the stream. Q, it's good to see you. Welcome in. Happy Sunday. How are you? I hope you're doing good. I hope everybody's doing good. I hope everybody had a lovely Saturday. Again, like, this is like a mini lecture crash course, okay? This isn't like super in depth. I want to do the topic justice, but also we only have so much time and we could literally do lectures upon lectures about science, but because we're just doing like a little tiny little thing, I'm not expecting this to go for like forever, but hopefully, fingers crossed. Sorry, I'm dying. You guys, I can keep you guys engaged and keep you guys wanting to hang out. The question of the day is the exam. Yeah, there's 20 questions on the exam and nobody has to purchase anything. The only caveat, unfortunately, with the quiz at the end is that Kahoot doesn't let me see who what player is who unless I pay for like a pro edition of Kahoot. So whenever you guys like sign in and do your little users names into the Kahoot, you'll have to tell me what your username is if you want to get credit, and then you could potentially win a prize. Because I physically can't figure out who it is. It gives me like an anonymous name that's linked to anybody. So you'll have to tell me in the chat if you'd like to get credit. If you just want to like play to play and you don't want to be, you know, known or something, and you're just trying to flex without trying to like show off or, you know, tell everybody who you are, be nameless, that's perfectly fine too. But the thing is that I won't be able to give out prizes if you don't give me your username and associate it with like with the little, because they give like really random names like Moose Anonymous or something, and it's very bizarre, but you get to decorate your little characters, so that's cool. That's the one perk. I don't like how Kahoot has changed. It's now like behind a lot of paywalls, but it is what it is, and it's fine. I still very much enjoy Kahoot, and we'll take it. We'll take it. We'll take what we can get. Why are we CRISPRing today? We are going to be CRISPRing today because, yeah, I hope I get Daddy Moose Knuckles for my randomness. You're not getting Daddy Moose Knuckles. Get out. So this was actually, wasn't it a, didn't we have it was a, we had so it was originally a community goal, I believe. And so we had decided we were going to do a science mini lecture instead of doing a show or movie science analysis like I've done in the past. So this is a little bit different. So I'm talking about like a specific topic or concept. And in this case, you guys voted on doing CRISPR and genome editing. I had a few different options. So this was the first one. It was gene therapy, stem cell research, bioremediation, liquid biopsies, and then mRNA therapeutics. So this is what won, and I'm really excited to talk about it because I think CRISPR is really cool. But I kind of was like, you know what? F it, we ball. Let's have a good time. We'll see what happens. I don't know. Kai, it's good to see you. Welcome in, welcome in. You Bill Nye tonight? I am Bill Nye. I'm gonna be Bill Nye, that spooky guy. It's gonna be great. I'm really excited. I hope that it's engaging and fun and you guys learn something. And it's like, granted, I know that a lot of this information is probably going to be, you know, stuff you guys already know, but we don't know, you know, where people lie in terms of their knowledge. So I like to kind of like keep everything ground level, have building blocks so that everybody's on the same page before we move on to other information, if that makes sense. I did disable the reward. So I've done a few science streams now, and it can get kind of, what's the word I'm looking for? Distracting. So it's just that, like, I love doing them and I like doing them with the rewards, and I thought about keeping on the redeems, but there's a lot of videos that I do want to show and like a lot of topics I want to touch, and because we're doing like a quiz at the end, I want to make sure that you guys aren't completely getting hi Nia, welcome in, welcome in. 1 more month for a year and a half. That's crazy. Welcome in, Nia. I hope you're doing so good. Happy Sunday. I just want to make sure that everybody is getting all of the information and we're not getting completely distracted, just because there's gonna be prizes at the end. There's gonna be a little prize at the end for the winner of the quiz. So I'm like, I might as well disable the awards so that we're not getting sidetracked, because you know how that was during last stream. I was getting sidetracked like horde. But it was funny. I really did enjoy myself. If you guys didn't watch Friday, I did a dating sim stream with Chickies, Tendies, I'm Cold Ramen, and Call Me Blip. It was really, really fun. But the thing was is that alerts were going off like crazy. And I was like, shoot, I'm gonna have to disable this for the science stream. CRISPR teachers at my old college, so I had to show up out of obligation. Out of obligation. That's crazy. Especially, okay, so also, full disclaimer, like, anybody who's expecting something that's like super, super in-depth, super like technical for all of this, it is very, very high level. This is going to be very high level. I just want to kind of introduce you guys to what CRISPR has to offer, and I'll be talking about genetics a little bit, and I think it'll be really fun just to kind of show you guys kind of a specific topic rather than going into like, oh, hey, we watched World War Z. Let's talk about it. Let's talk about the science that's in the movie, that kind of stuff. So it's just a different take on it. I haven't formatted streams like this at all. They've always been like a show or movie analysis. So bear with me. I'm trying. Yay, science! We can't derail. Ain't no way. No hot boys. Hot boys very distracting. Also, hi Bronner, hi Droidster. Welcome in, welcome in. I hope you guys are having lovely Sundays. I hope you guys are ready for some science. Isn't 35 months 1 month away from 3 years, not year and a half? I don't know. I didn't do the math. I wasn't doing the math. I just kind of read what it said. Did you hear about the world's first gene-edited baby took their first steps? So that's something that we are gonna kind of touch on. Designer babies is a kind of like an ethical thing we'll touch on here in this guy. No, those of you that don't know, I like micro, where I talk about bacteria, viruses. I don't really like ecology. That's one that I don't like. But I like micro, and I hate science. There's a reason why I went away from all math. I have my big brain hat on today, so I'm too prepared. Comedy's ready. Comedy's gonna point out all of the things. That being said, I'm waiting. I'm kind of waiting for everybody to kind of trickle in. Everybody's ready to go. Everybody got their notes out, okay? Because it's gonna be a big day for note taking. Because at the end, you got like 15-20 seconds to answer questions, and the faster you are at answering on the quiz, the more points you get, and the higher you are on the scale, on the leaderboard. So, just throwing that out there. The more you pay attention, the more you don't have to look at your notes, and the better you do on the quiz. Cloned his dead dog. Wonder what else he's planning. Huh? Are you serious? You're joking. That has to be a joke. That can't. No way. Designer babies are only bad. Can you imagine if your parents did your character creation screen instead of you? We're actually going to talk about that a little bit too. Yeah, it's crazy to think about, but yeah, this is kind of where that kind of stuff sort of comes into play. We'll be talking about that. Also, hi Moosey, welcome in. Happy Sunday. Anybody just popping in, again, I do have redeems off for today. I apologize, but I'm going to turn them off for today specifically just because it can be a little distracting. Again, and I want to make sure that everybody's getting all of the information they need so that they can do good on their quiz at the end, and you could potentially win a prize if you get first place. So I'm ready, but we're not ready. I'm kind of like, do I get started or do I wait a little bit longer? that's where I'm at right now. I'm trying to make sure that everybody has everything that they need and they're ready to go. Expectations will go crazy. You can't do music because I designed you for football. That's crazy. Yeah, it brings crazy interesting topics and ethics up when you're talking about CRISPR or genome editing in general. It's a very interesting topic, and I'm excited to see what you guys what you guys think and what you guys say. Optimized for sports ball. I'm actually serious. They definitely cloned his dog. Lots of people were weirded out by it. That's super bizarre. Okay. I'm gonna quickly say this, preface this. I find it interesting when we talk about clones and stuff like that, because I feel like a lot of us, yeah, you can probably like clone the same person down to a T, but a lot of our experiences shape who we are. So you'd have to like, I would think that you'd have to basically redo everything that you previously did with like a kid or like a dog or something, so that it's like the same kind of dog. But again, that's you can't replicate something like memories like that. You know what I'm saying? I don't know. I feel like consciousness is not something that you really can replicate, I feel like. You know what I'm talking about? I feel like that's a weird idea. Also, lady, welcome in. Happy Sunday. I hope you're doing good. It's Science Day. I hope you're doing well. Oh, let me see the tat. Sure, I can show you the tattoo. I got a tattoo. I think it's probably like, what, about almost 4 weeks at this point? And it wraps all the way around. Yeah. And she wraps around, but she was to cover up my cyst removal. And I said, I've been really wanting something like that. And I was wanting to get like a sleeve where it kind of wraps up and goes up my arm. And finally I found an artist that was able to do it. And beautiful. Chef's kiss. I have to go back in, they said like the 6-week mark is soon it should be fully healed. And then we'll do some touch-ups, because obviously on the hand, like we use our hands so much that I'm gonna have to get some touch-up on my fingies. But overall, I'm very happy with how it turned out. But there are some little spots here and there that I think that could do with a little touch-up. Did you think I made you 8 feet tall? Just for the ha-has, huh? They'll probably sell you the sports ball, baby, but if you don't pay your monthly subscription, they'll remotely turn off your child's sports ball. Would you bang your cloned things? Weird me out, because that's basically your identical twin. No, that is basically like, it's kind of in a sense like it's you. It's weird. I feel like this kind of topic brings up a lot of weird concepts and weird ethical things that it's bizarre. It's very odd. What's your opinion on Loki series when he fell in love with himself? Actually, not a bad one. That does feel weird too. Depends on how we describe the clone. Does it have all your memories and experiences and is you in every way? Then it's not an identical twin. It's just another you. But also, is it considered a twin if it's like, in a sense, like the multiverse, right? Like a spider clone, multiverse-ish. Technically, they have some of the same experiences, but they're like, everybody's a little bit different, or they are somewhat different in some way. What about that situation? Universes could be different enough that it isn't the same person. Yeah, it kind of does feel like it wouldn't be the same person. But that does bring up the question of like, are they the same? Are they different? Are they different enough? Talking designer baby clone, it would just have the same starting point. You could certainly study nature versus nurture. See, that's the other thing. That's what I was saying, is that like, it's not, I mean, unless you're actually like raising them and they're everything down to a T, having the same like nature nurture thing, you know, happening, is it really the exact same clone? I feel like there's a lot of steps along the way that your paths can deviate and they become a whole different person or individual, I guess you could say. Now they're no longer a clone. They're technically a clone, but they're not really the same person in a sense. Even though they're the same person. Yeah, I feel like very bizarre, very weird. I don't know. Do we get started? Are we ready? Should I go ahead and make a poll? Here, I'm gonna make a quick poll. Here, I'm making a quick poll. There we go. Okay. Just give me like the okay or not okay. I don't want to like draw anybody out of lurking either. So if you don't want to like comment in the chat saying that you're ready or not ready, please just like go ahead and just use the poll. Just tell me if you guys are ready to go. If you're not ready, perfectly fine. If you are ready, cool. And it's cool. Like I can yap for a little longer. Let's be honest. When it comes to multiverse, sometimes so disconnected that you can easily argue they aren't you, but if the only difference is that the version of me decided to not have a bagel and cream cheese this morning, that might be a little weird. No, I agree. No, I completely agree. It feels bizarre to think about. But again, I don't think that, like, if I were to consider it the multiverse, I think that those experiences are very different. And I wouldn't say it's quote-unquote me, if that makes sense. Oh, there was a book that I read a long time ago. And I'm trying to remember what it was called. Maybe you guys can like figure out what it is. Basically, the way that it went was there was a girl and she was like living life, basically like growing up, blah, blah, blah. And then she finds out that like she's been a clone this entire time. And her sister, or herself, I guess you could say, had previously like passed away, and her parents basically cloned her down to a T or something. And I'm trying to think of like what exactly happened, but basically she had a whole entire existential crisis. But they were going through the process of just like replicating every single memory that they had had with the first child, like the real child's, before the clone came along, just because they were trying to make her the same. And I think that if I remember correctly, it was something like, oh, you're not the same, even though we tried to do everything we possibly could to make you guys like similar. I don't recall. Okay, it looks like we're basically ready. Multiverse, hold on. Hold up. Pliv, it's good to see you! Welcome! Happy Sunday! No way I can be around for a science stream. You're here for a science stream! Let's go! We're about to get started. We're just talking about like clones and stuff, because it is, I mean, we're going to be talking about basically designer babies here in this, so I think it'll be interesting. So it'll bring up some interesting questions. We'll have some really cool conversations, I think. What kind of notes do I need for this? Dotted line. Up to you. Completely up to you of what you want to do for your notes. I think people are different types of learners. I'm not gonna say what you need to do one way or the other. It's gotta be The Handmaid's Tale for sure, 100%. I haven't even read The Handmaid's Tale. I wonder if I've heard good things about the book, and I don't know about the movie yet. The only thing that pops up, Anna's of the Infinite Power. Man, I wish I could remember. I don't know. It was just a very bizarre book, but I was super invested. But it was a book, and I just don't remember what it was about, like what was called, and I would recommend it if I could recall the name. But I just looked those up, and they don't look familiar to me, so I don't know. Maybe I'll have to like do some digging around, and maybe I can find it for you guys. Farming and oh yeah. No. Make sure that you goon on the side. Get your goons in. It's fine. I understand it's important. Just make sure that you're ready for the quiz at the end. Double identity or replica? Oh, hold on. It might be double identity. Hold on. I'm looking it up. Double identity book. Yep. No, it was a Haddix book. You are right. That is exactly the one. Uh-huh. That was the one. I remember this. I recommend it. I thought it was super interesting when I was younger. I think I read it. I don't know if you guys had this when you were a young child, a young fetus in school, where you had to reach so many like book reading points, where every book like equated to so many points, and you had to reach so many points by the end of the month or whatever. AR quizzes. Yeah, like the AR quizzes. Yeah. I think that's what I had. And basically you had like a little quiz at the end, and they would check your comprehension, make sure that you actually read the book and you weren't just lying. I think one time a friend and I were trying to like get into like get like a certain prize or something. And I think that we both each read like these really, really big books, and then we took each other's quizzes so that we got double the points. And so it was like, we were like, F it. I'll read a big book, you read a big book. It'll take us a little bit, but like by the time we finish, we both can just take the quiz for each other. And it was fine. It was okay. I'm cheating on those computers reading quizzes. I mean, the thing is, they made it easy. They made it easy to do it. I think there was only one time I actually did it though, because I was so afraid that we were gonna get caught. But the way that we made it sure that it was okay and that we didn't get caught was by each person actually checking out those books. So like I checked it out first and then the other person checked it out. So like you would go back and forth. So it didn't look like you were just like both at the same time. You read them both, quote unquote, and then you're both getting the quizzes done. No, it was like we beat the system, okay? All right? Nobody caught us. They can't get mad at me. I did that for kindergarten. I read 100 books in a month. In a month? What kind of books were you reading? I remember lots of cheating on those kids. I think that's the funniest thing, is how many people cheated on them. One time me and my friends swapped exams for 2 questions because the teacher left the room. Look at you, Emma. This is where we find out when the people cheated on their stuff. 2 to 3 points and like a 10-point book, so that I would have to stream of little points and then once every 2 weeks or so get a big bump of big points. I mean, if you can beat the system, beat the system. You know? Make it to your little pizza parties, really. Go get extra outside time. Let's be honest. I'm not gonna go tell on you guys. Literally that one time ever, and the one time I wrote a science equation on my arm, but that's it. Hold on. My thingy, ouchie, came out. Hold up. My earbuds. I was not a good student in high school, but you're a good student now, and that's what counts. You're gonna ace this test. All right, are we ready? Are we good to go? I think we're ready. I'm gonna put some tunes on. I promise you, it's not gonna be actual like music. It's just gonna be lo-fi, just so that we have some background noise, and it'll be fun. I don't know. I really am pleased with how this turned out, by the way. I think it looks so cute. I really like how the presentation looks. So hopefully you guys like it too. It gets cooler, I promise. There's a slide in particular that I am so like proud of how it looks. I was searching all over Canva trying to find like little diagrams and stuff, and I found like different stuff, and I like threw them together, and I was like, it was great. All right, you got your chicky nuggies ready to keep you engaged. I got you guys. All right. Okay. Let me drink some water before I jump into this hoe. Because let's be honest, I'm going to be talking a lot. Hopefully you guys had a good meal before you guys provided sustenance to the brain. Fingers crossed. Okay. So before we dive in, I always preface this the same way for every single one of my science streams. Ooh, that sounds really good. Yeah. Luckily you're a pro yapper, so lectures are right up your alley. It's the same thing. It's basically the same thing. I just get to talk about science for like, what, 3 hours? Probably less. I don't think it's gonna be that long. Hopefully not. Who knows? Maybe. All right. Again, I always preface every single science stream with this, just because I want people to be aware that I have a degree in microbiology, but I am not a geneticist. Nor am I an expert in CRISPR or genome editing. I will say that for anything that I do my science streams on, okay? All right? The science analysis I'm sharing today is just about the topic, and it's based on research I've gathered from various sources. It's just information I want to share with you all just to spark curiosity and just some learning. That's it. That's really the gist of it. It's just a mini lecture crash course. I'm barely scratching the surface of what these topics have to offer. There's a lot to unfold in these categories of things that I'm talking about, and we can talk days. There's entire lectures on this. There's classes on this stuff. So do you cite your stories so we can explore further if we want to. I do have sources on my own, but I would have to go back and grab that and put it in like the Discord if you really wanted them to, if you'd like me to. I didn't put them on the presentation, but I have them in my own notes, so I'd have to go through there and then go through. SMH fake news. Why are we hating on me? I'm sorry, I didn't want to show you guys things that you probably don't really care about at the end. But I can show you guys later. Okay. But again, just like throwing it out there, it's not an expert lecture. Honestly, you could probably find a lot of this information just by searching the web on your own. I've just basically put it in one place just so it's easy and quick for you guys to access, and this is just one spot where we can just talk about a crash course. That's really it. It's more of just a fun little mini lecture where we both learn together. I might not have all of the answers that you guys are looking for today, and that's okay. That's fine. This is just a learning session for both of us, so we can ask questions, explore ideas, deepen our understanding as a community, and if I don't know something, somebody in the chat might. And that's, I think, the beauty of this being a discussion and this being a live stream is the fact that we can both talk about it, and we can all talk about it, and we can both learn together. But really, I'm just here to do my best to explain things based on what I know. But again, it's just for fun. It's just for learning. There's just no... I think the biggest thing is there's absolutely no judgment on questions you ask or your current level of knowledge. The space is open, respectful, and supportive for everyone. So keep that in mind. If anyone tries to put someone down for their questions or makes jokes about their knowledge level, I will shut that down immediately with a ban. I don't play around with that. I don't condone putting anyone down for their level of knowledge at all. The space is open, and I want to keep this as welcoming and positive as I can. And I like to do these kind of streams just for funsies, and everyone, yeah, exactly. Everyone starts somewhere. You might not know everything, and that's the reason why I try to give a basic background on all of the topics that I talk about, so everyone has some groundwork before we get a little bit deeper. Again, this isn't a full course, and so it's just a friendly chat, so. But thank you guys so much, like, for being here. And I'm ready to have like a good, open, fun discussion where we're respectful. We have a good time. Okay? All right. I've seen you. I have seen you so much, and I hate it. Joke's on you. I won't fit in that locker. What do you mean, G-Vay? Where are you seeing me? Is it on TikTok? Is it on social media? God, I hope it's on social media. Is calling someone a nerd and shoving them in a metaphorical locker okay? As long as we're not, like, if I know it's a joke and we're just messing around, perfectly fine. Like, whatever. I can take a joke. But again, me personally, I can take jokes. I just don't want anybody in the chat to feel, like, let down or put down in any way. So, I feel like sometimes on the internet, things are misconstrued way too much. So, please be respectful of one another. I had a, last time during my stream, during my World War Z stream, somebody came in saying a really hateful thing, and it was very disrespectful. I immediately banned. I banned the person that was also with them, just so that, you know, there was no questions, if, ands, or buts. Like, I do not mess around when it comes to stuff like that. There's a lot of things that are brought up in terms of ethics in science, and that's something that I also don't mess around with. We can be respectful, and we can have discussions, and we can bring up plausible ideas of like the what if scenarios, but also at the end of the day, you can get very political with things, and I try very hard to lean on the side of not being too political with all of this stuff. Everybody has their own ideas, their own thoughts and mindsets on how they think about things, and I don't want that to be what my stream turns into. I want it to be just a fun little area where we all can have a good time and learn something new. And if that's something that you take further and go do your own research on, I feel like at the end of the day I just did my job. So I like to say in my dreams, but I mean, you went live like 5 days in a row. I did. No, I didn't stream yesterday. That's the one thing I didn't do. I didn't stream yesterday. I can take jokes, like being a Viagra sponsorship. That's one thing I definitely can do. So as long as I can still hear the lecture from the locker, I'm fine with it. Okay, there you go. All right. Okay, so we're gonna jump in and we're gonna talk about it. So, like I said, I didn't do my homework and like see where my camera sits, so I apologize. I'll read it to you though. And this isn't anything crazy. Like, you don't really need to see the whole thing. At the end of this, you should have somewhat of a basic understanding of like what genetics is, why it matters, DNA, genes and chromosomes, traits and inheritance, genetic mutations, predicting genetic outcomes, and then genome editing and CRISPR. I felt like I had to give you guys groundwork for like what genetics really involves. But again, it's the basics. Granted, I wanted to give you guys enough background so when we go into genome editing and CRISPR, you guys have at least some form of knowledge going in, and it's not just me like, hey, this is how it works. This is what CRISPR is, even though you don't know what, you don't actually know what a chromosome does or what a gene is, or we have the basic understanding of what DNA is, but like, what does it look like? What's the structure? So, how to grow your own Ryan Reynolds. Exactly. Mendel and his peas. Exactly. I also won't really be going into too much of the history behind all of this. I don't know. For me personally, it never really intrigued me too much as a student to know like what year what happened. I mean, I did that on my own, but like it being a question on the quiz wasn't really a fun thing for me. I was like, all right, I have to remember in like 1960 something. No, thank you. I'm good. So you're welcome. I didn't put any dates on the quiz. All right. So what is genetics really? At its core, can't wait to hear what CRISPR stands for in like 30 slides. Exactly. That's exactly it. At its core, genetics is the study of information. Everything living, every living thing just grows, develops, and functions based on instructions and stores it inside its cells. Sorry, I'm late to class, professor. Bummer. Tisk tisk. How are you, son? Hope you're doing good. Struggling to write, and I realized I can connect my tablet on my computer. Hey, yo, let's go!
Thank you, baby girl.
Thank you for the sub. Thank you for the sub. Door's locked. Gotta wait for a break. Does that make up for it? It does make up for it. It does. Like I mentioned, every little living thing grows, develops, and functions based on instructions stored inside its cells. So genetics is how we study those instructions, where they come from, how they're passed down, what they affect, and if you've ever wondered why you look the way that you do, or why certain traits run in families, that's just basically genetics at work. In a nutshell, that's it at the end of the day. I got the genetics for small pee-pee. Yeah, that is a thing. That's all right, and that's okay. You can blame your parents for that. You can blame genetics for that one. Of living and not growing and developing, my brother. Didn't you leave work early today? My client refused to comment at this time. Is crazy. Y'all are wild. But that's basically the gist of genetics. Throwing that out there just so you're aware. It's the study of hereditary. Hereditary. Yeah, heredity. My bad. Not the movie Hereditary. All right. Basically, that's the gist of it. Okay, this is the slide I'm really proud of. So I'm gonna not show my camera so you guys can see the beauty of this slide. Look at this beautiful slide. Okay, for one. All right. Just look at this hoe. Isn't she beautiful? I think it's so. Oops, sorry. Spoilers. It's a very, very pretty slide. So I'm gonna turn off my camera for this one so you guys can see what we're working with, okay? So there's a lot going on here, and we're gonna talk about all of this stuff, okay? And I have my cursor here, and you should be able to see the little blue dot, and I'll show you exactly what's happening, okay? So we're gonna start off with DNA. DNA stands for deoxyribonucleic acid, okay? And while that's kind of sounds intimidating, you can break it down, all right? So DNA is a really large molecule found inside the cells of all living things, and it carries genetic information that tells an organism how to grow, develop, and function. The really cool part about the like words in science is that if you break it down, you can basically like figure out what it means. So like the deoxyribose is the sugar, and then the nucleic acid is the macromolecule, and that's just what stores the genetic information. I'm late, but science! Bug, you were working. You get a pass. Sorry, I have my camera off specifically just so that everybody can see the beauty of the slide. Okay, and then on the left here, you can see this big old boy, and that's what we all know and love. So it's like a ladder, as you guys can see. If you look at DNA visually, it's often showed twisted, like this guy. See this guy right here? Like how it twisty twists. I actually made one on stream when I very first started streaming, and oh, that hoe made me so angry it wasn't spinning. Mom took me to McDonald's. God dang it. Y'all need to start getting some hall passes. Welcome in, Bug and Bertro. I hope you guys are having a good time. Having a lovely Sunday. See this guy right here? Okay. Sorry. But if you look at it, this ladder shape that's kind of like spinning, the twisted ladder shape is called a double helix, okay? And that's where this guy gets its name. The little DNA strand that we all know and love, okay? The sides of the ladder, so we're saying like this right here, see like the things that are like how it kind of wraps around. I'm talking about the sides here, that long boy right there. So the ladder's made of sugar and phosphate groups, and I'm not gonna go into too nitty gritty of like what that looks like because I think that's getting a little too into the weeds, but you can just think of that as the backbone, okay? All right, and then the rungs are like what's inside, right? That's exactly what you'd use to like get up on your ladder and start climbing, right? Those are made of something called nitrogen bases, and that's what you have right here. And that's why you're so sweet. She doubled my helix until I ATCG. Get out. And that's actually to my next point. Nitrogen bases. ATGCG. There are 4 nitrogen bases in DNA. There's adenine, thymine, cytosine, and guanine. Okay? Usually, you'll just see them shortened at this like ATCG though. The bases pair up in the same way. So A pairs with T and C pairs with G. So those pairs form the rungs of the DNA ladder. Okay? Does that make sense? Does that make sense to y'all? Do we have any questions so far? I just want to make sure that we're making sense here. Okay? I know what I'm talking around here. Do you know what you're talking about around here? Raise this hand. Yeah, no, please. Go ahead. If you have questions about it, let me know. Okay, F you, no. Take the phone to the bathroom. I knew he was gonna say that. Yeah, of course. Wait, can I get a thank you? Not the orgasms. Hold on, I'm going through. So, I knew he was gonna say that. Do we know why it pairs? So, I believe the short answer for this is, so it has to do with the hydrogen bonding, I believe, that goes between these. It's very crucial for maintaining the integrity of the genetic code, and then it minimizes the errors during DNA replication. I know that's a lot right there, but I don't want to like kind of confuse you guys, so I'll leave it at that to kind of answer. but there's bondage there, guys, okay? The bondage is important. So there's chemical interactions between the bases, ensuring that the A always goes with the T and the C always goes with the G, and it makes sure that you keep up with your same homie. Does that make sense? Basically they get freaky, but they're loyal, all right? I think that's the biggest thing that you need to remember, is that although they're getting freaky, they're loyal hoes. So there's that. Just throwing that out there. Is that it? Does that answer your question? Hopefully it does. And if I'm wrong and there's more to it, I apologize. I think I'm just trying to keep it very vague so I'm not getting too into the weeds. Bondage is important. There you go. Bondage is very important for your nitrogen bases, okay? I was always told that these hoes ain't loyal. Maybe the hoes that you're talking about, but these hoes remain loyal. Especially if you don't want problems. If you don't want problems, then it's not an issue, okay? But again, DNA is a large molecule found inside the cells of living things. It's made up of different elements that carry genetic information. And DNA is made up of 4 basic building blocks called nucleotides, okay? All right? Now let's talk about some nucleotides. All right. I will talk about RNA here in a few moments. I have kind of a slide that kind of touches like a little mini crash course on what RNA is and the difference between DNA and RNA. So, but first we have nucleotides that we're moving into now. So this is basically how the code is written, okay? So that's right here what we're talking about, okay? So each of these pairs is part of a unit. So each of these pairs right here, these are part of a unit called a nucleotide. And so a nucleotide is just a small building block of DNA. And DNA is made of many nucleotides linked together, and it's kind of like a chain. A good example of this is, you know, if DNA were like a necklace, each bead would be a nucleotide. And then if you don't like that analogy, another way to think about it is like Lego blocks. Every Lego piece has the same shape. So remember, like this guy, like this ladder here, it has the sugar and phosphate, but the color of the Lego pieces changes. So it's that A, T, C, G, and then the order of which you snap them together determines what you're building. So different orders of these little guys means different traits. Does that make sense? Hopefully that makes sense. I'm trying to give like different examples that could potentially be helpful. The order of the nucleotides along the DNA strand, like I mentioned, creates a genetic code. The order is what stores the information. Wait, sorry. I'm trying to catch up with chat. They ordered and built me into a baked bean. So the nitrogen bases are different than nucleotides. So the nitrogen bases are what the nucleotides are made of. So these little guys, the order of them changes. So the order of the nucleotides within the DNA strand forms a special genetic code. So like these guys make up the nucleotides. Does that make sense? I'm trying to be clear without being confusing. But basically, the nucleotides along the DNA strand creates a genetic code, and then the order is what stores information in DNA. Even though humans all have like the same 4 bases, the sequence is different from person to person. Okay? So like that's the reason why we're not all the same, is that all of these hoes in different orders can get crazy. So the 4 nucleotides are, you have, so the nitrogen bases are A, T, C, G, and then yeah, the nucleotides are, yeah. The only time is somewhat the same as with twins. Yeah, so like the time that it'll be the same is with twins, basically, like G-Bane mentioned. But of course, you know, they're not 100% identical, right? But of course, you know, they're made up of different elements that carry genetic information. So that's the biggest takeaway for the nucleotides, okay? But again, the sequence is different from person to person, but like as G-Bane mentioned, it's kind of gets a little finicky when it comes to twins. The DNA helix, so I've heard a couple different things on how, like, big this is. But, like, if you were to stretch it out, I believe I've heard somewhere around, like, 10 nanometers. But, like, if you were to put, like, all of your DNA, like, all together with all of your sequences, I'm pretty sure it's long, 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 long. Like, it's forever. I think somebody mentioned once that, like, it goes to the sun and back, like, 600 times, but I don't know if that's true or not. It's all the DNA that makes you up, exactly. I'd say it's average size. Get out. It's all crunched up. Yeah, so it's all crunched up into chromosomes, which I'll talk about here in a few minutes. Or here in a moment. Of a show where they found some DNA of a killer and they used that to figure out what they looked like. Oh. I don't think it was based in reality. Oh, interesting. I'd like to, like, that would be a really cool thing to, like, watch. Is long AF, if I remember correct. If you stretch it out, it would wrap the earth. Maybe it's all the DNA that makes... It's all the DNA that makes up you is what's, like, super, super long. But, just for, like, a normal little baby boy DNA strand, like, just one singular, I don't think it's, like, that big. But again, that doesn't make an entire person. It's just, like, a little dude. Just a little guy. But if you're doing, like, all of it, like, all of the DNA that makes up you... That's long. Long, long, long. DNA sequencing can be used to help determine features someone might have. It has been used for helping solve cold cases. Yes, yes. I just don't know how much DNA you actually need. That's the part that I'm iffy on. You can't hear a chromosome. Get out. Okay. So, again, like, just like letters from words and sentences, the sequence of nucleotides is the instructions. Okay? And then that code tells us a living thing how to grow, how to develop, and how its body functions at the most basic of ways, or like basic of terms. Okay? And so when we say DNA is an instruction manual, this is the language it's written in. Right? It's written in nucleotides. So basically, like, these little, like, the way that it's written, the nucleotides is like that instructions. Okay? Next, we're going to talk about a little bit about chromosomes. That's these guys right here. So now, of course, you know, DNA, like we mentioned, is extremely long, so it doesn't just float around freely. It's tightly packed into these structures called chromosomes, and that's what you see right here, this little guy. And you can think of DNA like a long piece of string. A chromosome is like winding that string neatly around a spool. So the DNA would be the string, and then the chromosome would be the neatly wound spool, or bundle, you should say, or I should say. This keeps the DNA from tangling or breaking. And so in humans, we have 46 DNA molecules organized into 23 pairs of chromosomes. So you have 46, and then there's 46, and then they're paired up into 23. And you get one chromosome from each parent. And that's why you're a mix of both. So, hold on, wait a minute. Give me a second. Let me show you with my hands, my fingies. You get one from mom, one from dad. Bam. So 1, you. And then it's just like, whoop, and then that makes up your little guy, okay? That makes you. I guess I can technically show my cam. We're done looking at the top of the screen. Unless you, well, hold on. I'll keep it closed in case people are still writing or like putting notes down. But that's roughly the situation with chromosomes, okay? Then I'm going to talk to you a little bit about the nucleus. And we know a little bit about the nucleus because the nucleus is the control center. And that's this guy right here. This little egg guy right here, that's the nucleus. And so chromosomes are found inside the nucleus, and you can kind of see them right there. They're all like just floating around in there, which you can kind of think of as like the control center of the cell. And this is where genetic information is stored and protected. And this information is what gets passed down from parents to children. Yes, and mom chromosomes are XX and dad chromosomes are XY. And I didn't go too in detail about mom and dad chromosomes just because I think that it kind of gets a little bit more into more detail about genetics, which we could probably talk about again forever, but I just gave you guys like a little something, okay? Mom can only have X, and dad is the one who determines if you get an X or a Y. Exactly. No, that is exactly the situation. I may have to stay after class. I'm on 4. Dense are your notes. I summarize things. I need to buy a new notebook. I think the one thing that I like to think of the nucleus as, that you can think of it as if you'd like to, is like a safe. The important documents, aka the DNA, are stored inside, and instructions are sent out when it's needed, and not everyone has direct access to this. And this just keeps information organized and secure. Okay? My sticky note is almost full of notes, and I'm just copying everything down word for word. I never learned note taking. I mean, it's okay. It happens. I think that I used to kind of be the same way when it came to taking notes. Okay. So before we get into the next slide, I'm just going to quickly like kind of talk about it. Genes, just so that we have like more of a groundwork, okay? Just so that you guys are familiar with what genes are. So genes are specific instructions, and you can kind of see that where I talk about it a little bit right here on this little guy here. And a gene is basically a segment of DNA that contains I got blue jeans, get out. I'm sorry. Okay. A gene basically is a segment of DNA that contains instructions for making a specific protein. And proteins are like the machines and tools inside your cells. So they build the structures, carry the signals, and run the chemical reactions your body needs to function. And you can think of it this way. DNA is the full instruction manual for an organism, and genes are the individual chapters or recipes inside that manual. And for example, there's a gene that helps determine your eye color, one that affects your blood type, one that influences how your body processes things like sugars or fats, stuff like that. My DNA is like an IKEA bed frame. I summarized genetics into study of heredity. There you go. There you go. Saw a movie where there was, the kids got telepathic powers, and when the FBI were questioning them, I thought the kid needed to send a pair of genes to future to save it from dystopia, and was confused why the little girl's tears were enough if they weren't genes. I love that. Shout out the genes that blessed me with these baby blues. There you go. IKEA bed frame instruction manual. You got it. You get it. Okay. It's all in a different language, and they're telling me to use a piece that I never received. But I think the really important point is that most traits aren't controlled by a single gene. Many traits like, for example, height, weight, or even how your brain works are influenced by multiple genes working together. And the environment plays a big role. As we've mentioned kind of earlier at the beginning before we started, genes are important, but they aren't the entire story. They come in very different versions. The thing is, like instructions are all pictures. What manual are you reading? I don't have genes. My parents once had an argument over whose genes were responsible for being a disappointment. Is crazy. But again, like, I think another thing that I would like for you guys to know, sorry, I just want to like make sure that I have it. So genes also come in versions called alleles, alleles. And for each gene, you inherit one allele from your mom and one from your dad. And then these combinations are what make each person unique. Okay? And then there's more to this, and we could probably talk more about this and break it down and get more into like the nitty gritty, but this mini lecture here, I'll put it in the chat just in case. Alleles. A-L-L-E-L-E-S. Like that. And so, again, like, just I think the biggest thing to know is that you get one from each parent. But again, like, this is just nitty gritty stuff. I'm not going to go into too much detail about alleles because I think that you can get a little bit more into like the woodworks. But I'm just trying to give you the framework of what we need when we talk about CRISPR and genome editing, okay? So to give you like a quick little recap of this slide, a gene is a specific stretch of DNA that contains instructions, usually for making a protein. Proteins do most of the work in the cell. They build structures, send signals, and run chemical reactions. And so genes influence things like eye color, blood type, height, and even disease risk. Okay? Does that mean I have some brown in my eye? Oh yeah, the heterochromia, it's so pretty. Ooh, how many genes are there? Ooh, I don't know about, like, genes within you, per se, but I know that the Human Genome Project has determined that humans have an estimated 30,000 genes. So, estimated. It's all estimated. So, that's what I do know. Okay. Hopefully this makes sense to you guys. That is what I have for DNA, nucleotides, chromosomes, and genes. Oh, and of course the nucleus. So that's where that is. And I'm going to give you guys basically a little mini crash course. It's very, very quick. I think I can show you guys my camera now, because I don't think that my camera covers this. Ah, it does cover it, mother F. Okay, hold on. I'm gonna make myself really tiny, okay? We're gonna make myself tiny, tiny up there. Okay. I think I have 4 pairs of jeans. I think anything and someone asked him who is the person who has DNA. Okay. All right. It's a very tiny spooky just because I feel like I'm a very expressive person, okay? All right. So RNA. So we think of RNA, so think of sorry, I'm having a stroke. DNA is long-term instruction manual for your body, okay? RNA is kind of like the working copy of those instructions. So what it does, DNA mostly stays protected inside the nucleus of the cells, but RNA's job is to carry the information from DNA to the rest of the cell. So the instructions can actually be used. So think of it as like a messenger. And that's the biggest takeaway, okay? Instead of taking the entire instruction manual, the cell makes a temporary copy and or just like a section that it needs, and that copy right there, that's just the RNA, okay? And very high level differences between the two. DNA is stored information long term, while RNA is short term. And then DNA stays mostly in one place, while RNA moves around the cell delivering instructions, okay? And there's different types of RNA. There's mRNA, tRNA, rRNA. And I'm not going to go into too much detail about each one of those because I don't think that it's something that we need to discuss right now. But that's roughly the situation with RNA and your quick little crash course. So I think the biggest takeaway is here is that it's like your messenger. It's like your, what's the word? Your little car. It's like your car. MR! That's what I heard. Might be tiny in size, but I have mighty personality, guys. Mighty personality. But basically, it often is described as, you know, the bridge of the gap between genetic information encoded in DNA and proteins that form the structure and function of living organisms. So I think that the biggest takeaway here is that try not to get too in the weeds about it. Just think of it as very high level for our instances, that it is taking code and basically making a copy of it from our DNA and then being able to transfer it over to things that it needs. Okay? And of course, RNA is only one strand. As you can see, like right here, this little guy. DNA is the double, and then RNA is the single. Yes, there are multiple. So there's messenger RNA, transfer RNA, and ribosomal RNA. And then the bases in RNA are adenine, uracil, guanine, and cytosine. So there is a little bit of a difference. If you remember in the previous slide, it's adenine, thymine, cytosine, guanine. And then for RNA, it's adenine, uracil, guanine, cytosine. So RNA is me holding the instruction manual while my wife screws the pieces together. In a sense, I guess you could think of it as that. I personally like to think of it as, hey, I have the instruction manual right here, but I'm just going to go ahead and copy it real quick, and then I'll give that instruction to your wife. I think to think of it as that. So yeah, thymine replaces uracil in this situation. The difference between the ribo and the deoxyribo, I believe it has to do with the way that it's composed up, like the backbone. As for deoxy versus ribo, so I just want to make sure that I say this right. That's why I'm looking it up. So both are 5 carbon sugars, but the key difference is that ribose contains an additional atom. So that's kind of what the difference is between the two. So they're a little bit different. And I'm trying to like, so the presence of that oxygen makes RNA more reactive and suitable for various different functions. And I don't want to get into like too much of the weeds, because then we're getting like way too nitty gritty of like the reasons why RNA is the way that it is, but that can go into like DNA replication and stuff like that, and that can get a little bit further. And then as for why thymine replaces uracil, and so I believe from what I remember, thymine is more stable than uracil, and it's because of a methyl group. And again, a lot of this is like things having to do with how the chemical reactions. So there's an additional like methyl group there, and so it makes it more stable. And because yeah, sorry, I'm trying to think. Yeah, so it's basically another reason of like why it's more stable. It enhances its resistance to chemical reactions for long-term storage, and it's just for the genetic information in the DNA. So you want something that's a little bit hardier, and that's what the thymine provides over the uracil. Does that make sense? Hopefully I'm answering questions correctly. like that you guys are able to understand. And that's roughly your crash course on what RNA is. But for our purposes, just try to think of it as like, hey, this is a messenger. And that's the biggest takeaway from here. Okay? All right. So that's the thing. I'm saying RNA as the messenger, but really RNA encompasses many different types of RNA. There's mRNA, which is the messenger RNA. There's transfer RNA, and there's ribosomal RNA. I'm thinking of it more of like a collective just genre of just RNA, but that encompasses mRNA, transfer RNA, rRNA. So like for our purposes today, just think of RNA as the messenger, because then once you start getting to like mRNA, tRNA, or rRNA, they all have like a little bit of different functions, but that's kind of not what we're trying to get at for this lecture, so I didn't want to like go too into the weeds about that. Yes, comedy. You got a question for me? Hopefully I'm doing an okay job explaining this. Yes, so the funny thing about that is that, yes, you do have DNA in all living things, but also some organisms contain RNA, but no DNA. And so this is where things get a little bit blurred lines, because you have organisms like viruses, right? Viruses aren't technically considered alive, but they do have there's RNA viruses, right? And it kind of like starts to relate back to like, is that actually a living thing? Or you can kind of get into the weeds a little bit. Does that make sense? Like, you can probably get into like the what is considered alive, right? So, but RNA is present in organisms, but DNA is primary hereditary material that supports like complete genetic blueprint for an organism. So if an organism doesn't necessarily need the whole picture, I think that they can get away with the RNA. It's like the blueprints. Yeah, organisms doesn't necessarily mean quote unquote alive in our situation. Does that make sense? But RNA is kind of considered like the intermediary between like genetic information and functional proteins. Yes, zombies. Exactly. You get it. All right. So next I'm going to talk to you a little bit about traits and inheritance. So for traits and inheritance, traits are the outcomes of our genetic instructions. And some of these might be physical, like hair color, eye color, and others are functional. Don't know why my camera just gave out on me right there. Sorry. Please hold. My camera just said, I'm good, thanks. Here we are. We're good. Don't know what that was about. My bad. Okay. Ruh-roh. We're good. We're back. Others are functional. So, of course, like I mentioned, some traits are physical, some are functional, and then the functionals affect how your body works. So, for example, whether you can digest lactose, or how your body, your immune system reacts to infections, stuff like that. And so, while all traits are influenced by genes, they are not determined by genes alone, like kind of what we mentioned before. Environment does play a big role. So genetics isn't quote unquote destiny, okay? Big example of this that I like to talk about is that some people have genes to have super, super strong muscles, right? But without proper nutrition and exercise, those muscles won't fully develop. And so similarly, if a person might have genes to have, a taller height, if they experience malnutrition during childhood, they may not reach their full potential. So it's like your genes only go so far. Wishing I could hang, but I'm still working. Look, sciencey AF. Though, good job. All good, Lars. I hope work goes well. Thank you for popping in. So I think that's the biggest takeaway, is that, yeah, we do have genes and traits that, like, we are, you know, born to have, but a lot of our environment shapes who we are. And so you might have these traits that could make you X, but because of Y, you don't look the way that you do or function the way that you're, you know, for whatever reason. Okay? And so that's kind of roughly where this one comes into play. Oh, shoot. Can you say this? Please hold. My capture card is being a little funky. There we go. Got it. It didn't just switch slides. Okay. So that's kind of the big picture with traits and inheritance. I think the biggest thing that we can think about also is Punnett squares. We love Punnett squares. We know how they work, but the thing is, it's a lot more complicated than this. Yes, we can try to predict a lot of the things that happen, but again, like, at the end of the day, it's not always going to be what we expect. Y'all educated in here? Yeah, we are. Welcome in, Trigger. Welcome. I hope you're doing so good. Happy Sunday. We're just talking about kind of the base work for genetics, and before we start talking about, like, CRISPR and genome editing. And so chromosomes have genetic code, and the code is instructions to make proteins, and proteins determines physical traits. I know my protein powder was worth something. Exactly. Hi, Xander. Welcome in as well. I hope you guys are having a lovely Sunday. We are going into nitty-gritty details. Well, not nitty-gritty. Probably, like, base knowledge of, you know, genetics, giving some groundwork before we start discussing CRISPR and genome editing. And this is like just a mini lecture crash course on all of that, really. But to study inheritance, scientists often use like Punnett squares, like, as we all know, and we all love them, and some people really hate them. To visualize the probability of passing traits from parents to offsprings. So, for example, one parent carries a gene of brown eyes and one other for blue. So the Punnett squares can show the likely combinations in their children. So a dominant trait is a trait that is one that shows up in an organism even if only one copy of the gene has it. Okay? And an example of this would be, like, you know, if an allele for brown eyes is dominant. So see this right here? This guy. This is like the example I'm giving right here. You only need one brown eye allele to have brown eyes. So you can have a recessive trait, and I'll talk about that here in a second. You can have a recessive trait for blue eyes, but the parent or the person has brown eyes. And the recessive trait is essentially a trait only shows up if an organism has two copies of that recessive allele from each parent. So in this case, recessive is blue. And so you have a parent with blue eyes and a parent with brown eyes. And then when you know, cross them, you have the big B, little b. And then obviously that means that the dominant trait is going to show as brown. And then of course you have big B, little b, and then big B, little b. And then of course at the end, big B, little b. And so if a parent has brown eyes and another parent has blue eyes, then clearly for this one, 100% of the kids would have brown eyes. And then of course there's a situation where you have brown eyes, but one of the parents the parent with brown eyes has a recessive trait for blue eyes. Then you have a big B, little b, and then you have another parent with little b, which means they have blue eyes. Then if you cross these two, there's a 50% chance of the offspring having brown eyes or blue eyes. And then lastly, if you have a parent that has both parents have recessive traits for blue eyes, so they both have brown but recessive traits for blues, then there's a 75% chance of that offspring having brown eyes and only a 25% chance of that child having blue eyes. And then, as you can see, 50% of those kids would have a recessive trait for blue. So, all brown eyes, but I came out with green eyes. So it could have very well been that they had recessive traits. But again, like, this is just basic Punnett squares. Genetics is very more complicated than this. So there's a lot more that goes into like play when stuff like this is happening in the background. So, but this is like a really like quick way to kind of look. It's like with Mendel's peas. If you know Mendel's peas, he just crossed a whole bunch of peas together to figure out, you know, dominant traits versus recessive traits and stuff like that. But reminder and note, while the section of DNA is called a gene, a specific pattern in a gene is called an allele. So there's your definition if you needed it to write it down. But yeah, that's the biggest takeaway here for like dominant traits versus recessive traits. Personally, I really love doing Punnett squares when I was in school, but I understood when people didn't. It's when you get into the dihybrid Punnett squares when things get a little bit crazy. I didn't put that here, but I'll quickly show you just like an example of a dihybrid just so that you can see it. So as you can see here, a dihybrid, it's like you have two dominant traits for this, and then you have like heterozygous, and things get a little bit in the weeds here, but that's how like the Punnett squares can come a little bit more involved, and it can get a little bit more, I guess you could say, complicated, if that makes sense. I'm trying to download traits in the background, but I'm low on RAM. Okay. But that's roughly the situation, if that makes sense. Jen said, welcome in. Welcome. Was not expecting science/biology, but I love it. Yes, we were doing a science stream. Anybody who's just popping in right now, basically the situation is we had a science stream that was supposed to be so it's supposed to be done. I think we redeemed it at the end of last year. And basically I left it up to everybody to say, hey, do you want to do another science movie analysis, or do you want to do a situation where we just talk about a topic? And everybody chose the topic this time. And I've done in the past science streams where we talked about like World War Z, The Last of Us, Myth-busting Mythbusters. It was stuff like that. It was really, really fun. But this time we decided to take a different route, and we're talking about CRISPR and genome editing today. And it's been really good time. And anybody just popping in that isn't familiar with my background, I have a background in microbiology with a minor in chemistry. And although I'm not a geneticist or an expert in CRISPR or genome editing, I don't know. Sometimes I just like to have like little science streams where I talk a little bit about the other side of things that I do. I currently do work with clinical research, so I do clinical trials, and yeah, just I've been in a lot of different areas of science, so sometimes I like to offer up a different side of knowledge that I know. Hi, Coda. I'm still at work, and I'm sad to be missing the science stream. It's okay. It happens. I hope you have a good day today. Coda, I appreciate you popping in. They got thrown off by my green eyes. Didn't know whether to speak Spanish to me. I constantly am assumed that I'm not Mexican, even though I look completely white. So there's that. Okay, I do have some videos. I've been doing a lot of talking, and I want to give you guys like little videos here and there that isn't just me yapping at you, some like kind of side stuff. And I think that this is it's just a little mini genetics 101 that I think is a really cool video. So I'll show you guys this one, and then I'll do a little bit more yapping, okay? And I'm gonna pause my stuff. I'm gonna pause my stuff, and then I'm gonna turn off my camera so that you guys can see this a little bit better. But do you look at the corner? Fun facts, I did talk about this a little bit earlier, but the Human Genome Project has determined that humans have an estimated 30,000 genes. So 30,000. Which is crazy. Insane. We can nerd out. Yeah, I love it. Oh, sorry.
Genetics.
My bad. I'm turning off the wrong thing. I meant to turn off my camera, not the capture cam. Please hold, please hold. Here we go. There's that. And then I'll be quiet, and then you guys can watch this, okay? All right. Here it is.
Genetics helps us understand the biological programming behind all life forms. But what exactly is the science of genetics? And what does its future hold? Genetics is the study of heredity, the expression of traits and how they are passed from generation to generation. For thousands of years, humans have observed this inheritance of traits and implemented their knowledge to breed and domesticate plants and animals. However, the science behind inheritance was only starting to be understood in the mid-19th century. Around 1865, Austrian monk and botanist Gregor Mendel published the results of his hybridization studies of pea plants. In his findings, he noted the role of factors that influence the expression of traits. These factors later became known as genes. Each human has between 20,000 and 25,000 genes. This collection, called a genome, determines a person's traits by influencing factors on a cellular level. Genetic information is stored in every cell's nucleus. Structures called chromosomes carry this information in the form of deoxyribonucleic acid, or DNA. DNA is a double helix of nucleotides, chemical compounds composed of sugar and phosphate molecules, along with the bases thymine, adenine, guanine, and cytosine. These segments of DNA are what we call genes, and it is within those genes that chemical compounds provide the coding for all information about a person's inherited traits. Human cells contain so much DNA to carry this large amount of information that, if unraveled, the DNA in each cell would be over 6 feet long. At the turn of the 21st century, an international effort to decode human DNA was launched. Called the Human Genome Project, it ended up identifying about 99% of the entire human genetic sequence.
A revolution in medical science whose implications far surpass even the discovery of antibiotics.
Discoveries in genetics research have unearthed tremendous opportunities in medicine, such as genetic testing and the manipulation of genes. But with these opportunities come risks and ethical questions. And finding the answers to those questions may be the next stage of our understanding of genetics.
Okay. And that was a little video I had on like little genetics 101 for you guys. Hope you guys like that. Just a, like a little something something, you know what I'm saying? Just a little something something. So you don't have to hear me yapping and I can get some wah-wah. But welcome in, Crazy Beards. Welcome in, Savvy. Welcome in, everybody. But yeah, that's just a little recap of genetics, kind of some things that we already discussed. And we're gonna get into some more fun things. Sounds like a dystopian project. Honestly, it's funny because when I was younger, I wanted to do work on the Human Genome Project. I was like, oh, I'm gonna get in on that. And now I'm like, I'm good, thanks. I'd rather not. But Human Genome Project sounds really dystopian, though, for sure. Sounds like a start of Resident Evil. It really does sound like it. The bad guys completed the Human Genome Project and used to develop bioweapons to defeat the good guys and enslave the world. Hello? That's crazy. Oh my gosh. Okay. Now this is when we start talking about more into like mutations, genome editing, and a little bit more about CRISPR, okay? Bear with me. If you're just popping in, I know that you probably missed a lot of the groundwork, so I apologize. But there's a lot there that's just basic, but I hope that it doesn't hurt you guys too much on the little quiz at the end. I do have a quiz at the end of the science stream that you guys can take. There is a prize for somebody who gets first place. The faster you are at answering the questions, the higher you are on the leaderboard. It's a Kahoot. So just throwing that out there. If you'd like to participate, you can at the end, or you can just stay anonymous. The other thing, the caveat that I have with my Kahoot is that unfortunately I can't just like put your guys' names in there. It makes it anonymous. So you'll have to tell me in the chat who you are within the quiz so that I know where you are on the leaderboard, unfortunately. But I had to pay extra. Kahoot now has like paywalls where like I can't even see who is doing what. So it sucks, but if you just want to play, you can. But if you want to try to like work towards getting a little prize, then you'll have to tell me what's your name before we start. Her mutations, by the way, so if you have dimples, you're a mutant. That's crazy. Seen enough movies and played enough Resident Evil games to be like, maybe the big company with spooky project name is probably the next Umbrella Corps. Yep, there you go. That's it. Okay, now we're gonna talk about genetic mutations, okay? We now have a basic understanding of DNA and genes and how traits are passed down. So let's talk about what happens when the instructions themselves change. So these changes are called mutations, and a mutation is just simply a change in the DNA sequence. That's basically it. It doesn't have to be scary. It's just a change in letters of the DNA code. So mutations can happen in a few different ways. Oh, sorry. Let me turn on my music again. There we go. It can happen in a few different ways. It can be, sometimes they happen naturally when the cell is copied. And that can just be through, not the who up getting mutated right now. Get out. It can happen naturally when cells copy during DNA, cell division. And I didn't go into too much detail about cell division, but it can be in just an error in replication, DNA replication. It can also be exposure to mutagens, so that can be like radioactive substances, x-rays, ultraviolet radiation, and certain chemicals, so that's another one, or viral infections in other infectious agents, and that can cause them as well. Mutations can affect a single letter in the DNA sequence or larger sections, and that can change how a gene works. So there are different types of mutations, and there is a substitution, there's an insertion, or there's deletion. And the differences between these is that substitution is when DNA is swapped for another. Insertion is a DNA letter gets added. Sorry, it's one DNA letter, apologies. And then deletion is DNA letter gets removed. So because here, let me preface by saying for like cancer research. So cancer research and radiation. So you have, you might already know this, but cancer is the result of a mutation, if you guys are aware. So, basically, the way that radiation works is to try to kind of counteract the mutation that's already occurring. Does that make sense? So, like, to be a little bit more specific about it, it's basically, it works by damaging the DNA of cancer cells. And so it prevents them from growing and dividing and ultimately causing them to die so that it's not further happening. Because it's already, it basically messes up the mutation. Exactly, Q. Does that make sense? Sorry, I'm just like looking at the chat because I'm like, hopefully I made that clear of like, I explained that well enough. Giving radiation to cancer, and now you have radiated cancer. But basically, we're just trying to kill those cells. But the problem with radiation is that you ultimately can be killing off healthy cells as well. It's kind of like, I'm just going to relate it somewhat to, like, mycology real quick. Don't think of it, like, in the same thing, the same. It's just, like, just an analogy, sort of. So with mycology, antifungal medications. The problem with antifungals is that we are very, very similar body composition-wise to fungi. So much so that when you use antifungals, you're basically hurting us as well as the fungus that's growing inside the host. So it's kind of like, in a sense, the same thing where radiation can hurt the host as well. Can radiotherapy make the cancer stronger? That's... let me look. Make cancer stronger. It says that there was a study done at University of Chicago Medicine, reveals that radiation therapy can spur growth in untreated metastatic tumors. So maybe in those situations? That's fully sci-fi. But they're definitely duplicating very rapidly. Exactly. So it's just stuff like that. Like, you know, mutations are just changes in the DNA. Some are neutral, some are harmful, and some are beneficial. And they are a natural part and very important part of life. So I think that's the biggest thing. The changes can have different effects. Some mutations do nothing at all. The genes are just fine. More Wolverine, but yeah. Some are just fine. Others can cause disease or disorders, and sometimes mutations can even be beneficial, giving an organism an advantage in the environment. Mutations are the raw material for evolution. That's why we evolve, because of mutations. An analogy that we could maybe like use, I'm gonna relate it back to like the recipe analogy, right? For DNA recipe analogy. If you change one ingredient, the outcome might taste a little different. It might ruin the dish, or it might be better. Mutations are like those changes to the recipe. So some might have no effect, and some might be unexpectedly useful. Why mutations matter? Mutations explain kind of like why siblings can look similar but not identical. So they help us understand genetic diseases and how traits evolve over time. They also set the stage for genome editing. And because if we understand how DNA changes naturally, we can learn how to change it intentionally. And so in short, mutations are just changes in DNA. Some can be neutral, harmful, or beneficial. I baked a cake and mixed up salt and sugar. It was catastrophic. But yeah, that's roughly at the end of the day, those are the overall basic key takeaways for genetic mutation, okay? All right. Are we ready? We're going to move on. Now we're going to get into some really cool stuff. We're going into genome editing now. Okay? Bear with me. This is the part where things can get a little bit confusing, okay? I'm going to try to break this down as well as I can. Also, I found out there was things that I can do with Canva, so if you're not paying attention, just give you a little... I can just do some bubbles on stream, just so I can get your attention again. Bear with me here, okay? Because this is where things can get a little in the weeds. Okay, we understand what genes are, how they influence traits. Now let's talk about genome editing, okay? It's a broad term that means intentionally changing DNA. It's like jingling keys. It's like the jingle jingle, but it's like bubble bubble. Bubble bubble. Pay attention, pay attention. I found it on TikTok. The little jingle jingle animation. Just, hey, pay attention. But yeah, basically, in broad terms, genome editing means that we're intentionally changing DNA, okay? Scientists can add, remove, or modify specific genes to change how cells behave. So instead of just observing DNA, genome editing allows us to actively edit the instructions themselves, okay? Hopefully you're sticking with me here. So what can genome editing do? So it can fix genes that cause disease, it can turn genes on and off, or it could help cells behave differently. Okay? So studies show how genes work by changing them and observing the results, okay? This right here, I'm going to talk about this here in a moment, so just bear with me, okay? It's important to note that genome editing doesn't always mean curing something. Sometimes it's just simply to learn how a gene functions. We don't always do science just to figure out how to just solve this cure or whatever problem. Sometimes we need to do the base work just to figure out, hey, this does this, and that means that ultimately this is a building block so that we can solve this problem. And I think that's something that's really cool about like the science behind this. Okay? All right. An example that I can give you is like fixing a faulty instruction. Imagine a gene that gives instructions for making a protein, but there's a small mistake in that gene. Because of that mistake, the protein doesn't work properly and causes disease. Genome editing can correct that and that mistake so that the cell can make the protein correctly again. So that's one example of how it could be applicable. I just realized I can just screenshot the slide and paste. See, you could just do that. You can just take a picture and paste it. Another example would be turning a gene off. So some genes are harmful and only because they're active when they shouldn't be. So genome editing can be like a light switch where we turn off a gene so it doesn't cause more problems or cause any problems, right? And then the last thing another example that I'll give you is adding helpful instructions. So in some cases, scientists can add a new piece of DNA that helps cells do something beneficial, like making them better at fighting a disease. So giving those the instructions. Some real life kind of applications, I guess you could say, would be like treating genetic disorders, cancer research, developing disease-resistant crops, studying inherited traits, which we'll talk a little bit more about real-world applications later, but these are just some vague examples, okay? All right. Now, I'm going to talk to you about how genome editing works, and this is where things get a little bit funky, okay? Bear with me, okay? Bubbles. I think the big key thing to remember is that genome editing is the concept. It's the goal of changing DNA. There are different tools and techniques that can be used to do the genome editing. And one of those big tools is that what we're going to discuss is CRISPR. And we'll talk about that next. But I'm going to talk about you how genome editing works first. Okay? Yes, genome editing is used in vaccine research as well. And I do have like real world applications where I can kind of talk to you guys a little bit more of like when this situation was sort of utilized. So, genome editing, all right? First, scientists use something called a DNA cutter, and DNA cutters are just, the other term for it is nuclease. It's also known as a nuclease. You can think of it kind of as like a molecular pair of scissors, okay? Now, the scissors don't just cut randomly. They are guided to a very specific location in the DNA called a target site. And this ensures that the edit doesn't just happen all willy-nilly. It edits and happens in the correct place. And it just... Okay? Next, once the DNA cutter reaches the target site, it locks onto the DNA. So as you can see here, see, this is where it's locating the DNA and like the cutters and stuff. And then it locks on, it docks. It's docking. It's one of the docking bros, okay? But once it reaches the target site, it locks onto the DNA and makes a cut through the DNA strand. The cut, again, it's intentional. It's a key step that allows changes to happen. And after the DNA is cut, the cell notices the break and immediately tries to repair it. The cell can fix the DNA in different ways. Sometimes it repairs the break on its own, which can slightly change the gene. Other times, it's scientists providing a repair template, which lets the cell add or replace specific DNA instructions. So this is how genes can be modified, removed, or even inserted. Okay? Finally, once the DNA is repaired, the genome is now considered edited. However, it's important to know that genome editing isn't always perfect. Because cells do the repairing themselves, unintended changes can sometimes recur, which may lead to unexpected effects. So the big takeaway here is that overall, genome editing works by cutting DNA at specific locations and letting the cell's natural repair system kind of do its thing and create those changes. Those changes are what we call genome edits. Okay? All right? Does that make sense? Hopefully that summarized it enough where it's broken down, where it's digestible, and it's not too in the weeds of what exactly is happening. But I hope that was okay, and we were all on the same page for what happens, how it happens. Okay. No one's saying anything, so I'm just going to assume we are okay. I think an analogy that would be really cool for us to use here is that genome editing is like editing a document. And remember how I mentioned how CRISPR is a form of genome editing? CRISPR is like a word processor. So we can think of it like kind of like Google Docs, right? It makes edits that are precise and fast, which I'll talk a little bit more about that here in a moment. God, this feels like a college class again. I'm sorry. I just want to make sure that everything's okay. I'm sorry. No one's saying anything, so I'm just gonna assume it's okay. I assume I'm all right. I don't want to be too much, but I also want to make sure that I'm describing okay. That I place my face in his tummy so that I can that he can explain it best. Exactly. No, if he can explain it, he can explain it. But yeah, you can think of genome editing as like deliberately editing the DNA rather than waiting for random mutations to happen. Okay? All right. That being said, I'm going to talk about CRISPR now. You guys ready for CRISPR? I'm so excited for CRISPR. Y'all don't understand. CRISPR is really, really cool. I worked in a lab, and one of my lab mates actually was starting to work with CRISPR as I was kind of transitioning out, going to a different place. But he was working on CRISPR for mycology, and it was really, really cool, the work that he was doing. And that was what I want to say. That was probably like maybe like 4 years ago, 3 years ago. I don't even remember, but it was really cool. Yes, comedy. What's the question? Before I get into CRISPR. But I do remember like CRISPR being like, when it started to become bigger. Is CRISPR or a process? I don't think I quite understand the... Oh, is it a machine or a process? So it is... It's kind of, in a sense, like a genome editing technology, if that makes sense. It's kind of like research that they've been doing, and it's honestly like crazy stuff that can revolutionize the way that we do like genome editing. And it's a type of genome editing that we can do. But give me a moment. I'm gonna give you guys like, I'll kind of discuss this slide here in a moment. I'll talk about a little bit more about CRISPR, but I just wanted to like talk about the questions. Is genome editing something that is ever done with humans, or is it only smaller organisms? So yeah, we actually are reaching the stage where we are doing work on humans. I do have a real world application that is a video at the end that I'll show you guys. And it is really cool of like things that we're working on. It's interesting. I don't know if we've actually, like, I can't say for a fact if we've done anything. No, we have done something. Apologies. It's in one of the videos that I have. What does palindromic mean in CRISPR? So in this situation, which I'll talk about, so CRISPR is short for clustered, regularly interspaced, short palindromic repeats. That's a mouthful. So that's why we shorten that up and we say CRISPR. Palindromic repeats are sequences in DNA that read the same forwards and backwards. And they play like a really crucial role in genetic functions and enzyme function recognition. So it's a really, really like big mouthful of a name. But CRISPR is a genome editing technology that allows scientists to make very precise changes to DNA. That there is a walking gene-edited baby out there. It's crazy, the things that CRISPR can do. Granted, what we know about CRISPR and the full potential of CRISPR, completely different. Like, we barely know enough about CRISPR right now and the potential of what it can offer. Insane. I can't even imagine what, like, a decade or 2 decades from now, how much we'll accomplish. Okay. What makes CRISPR really special is that it works like GPS guided scissors. Instead of cutting DNA randomly, CRISPR is programmed to get one exact location in the genome and cut. I think I remember hearing about CRISPR. CRISPR is really cool, honestly. I think that this is something that, like, oh man, it could revolutionize like so much. Okay. How it works, okay? We're gonna talk about how it works, okay? First, we find a target. So first a protein. There's a protein called Cas9. Cas9 is like the biggest one here that we're gonna talk about. Hi, Ghost, welcome in. Yeah, we're talking about CRISPR and genome editing. Welcome, welcome. We're just about to jump into it, talk about CRISPR. We did a lot of groundwork talking about what genetics is, DNA, nucleotides, chromosomes, nucleus, genes, RNA, stuff like that. But now we're talking about CRISPR. And so good. So good. I love it. Okay, years ago, I remember them saying they're studying how bacteria change their DNA so that we can do it. Yes. Hi, Jess. Welcome in. Welcome in. Anybody just popping in, I apologize. I do have, and all redeems off today, just so that we can talk about science. In the past, I've done science streams where it's just a little bit distracting. And I decided to turn them off because we have a quiz at the end of this. And if people get all of the questions right, then you could potentially win a prize. We're going to be doing a little Kahoot at the end. But we just did a lot of groundwork. It's kind of like the building blocks of the knowledge of CRISPR and genome editing. And now we're actually going into CRISPR. And again, this is just like a mini lecture and a crash course on what CRISPR and genome editing has to offer. It's not all of it. There's no way I could talk about all of it in like one stream. So bear with me, okay? Okay, like I mentioned, CRISPR is short for clustered, regularly interspaced short palindromic repeats. And it is just genome editing technology that allows scientists to make very precise changes to DNA, okay? What makes it special is that it's like GPS guided scissors. And instead of just cutting randomly, it's programmed to cut one exact location in the genome and just say, right there, let's do it. And so how it works, and we're going to talk about Cas9. I'm not going to go too much into the nitty gritty details about Cas9, but it is really cool, okay? A protein called Cas9 teams up with a piece of guide RNA. Remember that the guide RNA acts like kind of like an address label. It's like the messenger, right? So it tells Cas9 where exactly it needs to go go in the DNA, okay? So it's Cas9 is like, in a sense, like the boy doing the work with all of the information, and then RNA is like, hey, I know where to go, I got you. So together, the Cas9 and RNA form a search team that move through the cell looking for a DNA sequence that matches the guide, okay? Then we bind to the DNA. So when the guide RNA finds a matching DNA sequence, the Cas9 locks onto the spot in the genome. And this ensures that the cut happens at the correct and intended location, okay? All right, that's for binding. Then the cutting, once it's attached, Cas9 acts like those molecular scissors and cuts both strands of the DNA at that location. And then this cut allows genome editing to happen. So just like we saw earlier with genome editing in general, okay? Then we have the editing during repair, okay? So for this, after DNA is cut, the cell, like I mentioned, tries to repair that break. And so at this point, the gene might be disrupted and turned off. Our scientists can insert programmed DNA to add or change the instructions, okay? So this is like what you see right here. So going right in, okay? Either way, once the DNA is repaired, the genome has been edited. The big picture takeaway from this is that CRISPR is not different from genome editing. It's a tool used to do genome editing. So genome editing is ultimately the goal, right? And CRISPR is just one of the most powerful ways to achieve said goal. And it's because it is so precise. Okay. How does it know where to go? It's just trying to. So it's that RNA. Remember how RNA is like a copy of your DNA? It's basically saying, hey, I'm looking for this specifically, and RNA does all of the movement. So it's kind of like it has your Cas9 attached to it, and it says, all right, let's go look around and let's try to find exactly what matches this specific thing. And then Cas9 says, all right, swoop in, I got you right there. And so hopefully that answers your question. Cas9 walks over to the mailman and goes, hey, where's the gene? The mailman goes, follow me. Yeah, it's roughly like that. Cas9 is manufactured RNA. I wouldn't say that, no. It's just kind of like a team. So RNA is part of it, and then Cas9 protein goes with it to get to where it needs to go. They're just like a tag team. Does that make sense? Is Cas9 a naturally occurring protein? That one, so I know that, like, of course, it's naturally occurring. Yes. But it's actually it derives from a bacterial immune defense mechanism. And I'll talk about that, or we'll see a little bit more about that later, but it derives from a bacteria immune defense mechanism. But the system evolved in bacteria to protect them from viruses by inserting pieces of, like, DNA into their host genome, creating, like, a sequence basically as, like, CRISPR. But that's where it derives from bacteria. It's a bacteria immune defense mechanism. So it is technically naturally occurring, but we've taken it, if that makes sense. Okay. But I think that the big thing, Cas9 is like a tool, but on its own, it doesn't know where to go. That's why it needs the RNA. So the guide RNA gives Cas9 directions, and then together they have they have what's known as the CRISPR complex. Okay, hopefully, like, that kind of clarifies. So the guide RNA is short and precise, and it's essentially a copy of the target location written in RNA form. Okay, I want to make sure that, like, I'm covering that, like, Cas9 is the tool, but it doesn't know where to go or what to do. RNA is how we get it to where it needs to go. Okay. Okay. I think that's roughly the gist of it. I want to make sure that I answer any questions if you guys have any, but I have a video after this to kind of help discuss this further. Okay. So hopefully this helps kind of explain a little bit more if what I'm saying doesn't break it down enough. Okay. I'm going to turn off my camera. I'm going to turn off my camera, and it's going to also explain this more. Like Cas9 and how, like, we can get it to do what it wants. So I think this might actually be a better way to explain it, because maybe, like, I'm trying to explain, but I don't know if I'm quite getting there. But have this video, and if this doesn't quite answer your question, Comedy, then I'll answer in a different way. Okay?
From the smallest single-celled organism to the largest creatures on Earth, every living thing is defined by its genes. The DNA contained in our genes acts like an instruction manual for our cells. 4 building blocks called bases are strung together in precise sequences, which tell the cell how to behave and form the basis for our every trait. But with recent advancements in gene editing tools, scientists can change an organism's fundamental features in record time. They can engineer drought-resistant crops and create apples that don't brown. They might even prevent the spread of infectious outbreaks and develop cures for genetic diseases. CRISPR is the fastest, easiest, and cheapest of the gene editing tools responsible for this new wave of science. But where did this medical marvel come from? How does it work? And what can it do? Surprisingly, CRISPR is actually a natural process that's long functioned as a bacterial immune system. Originally found defending single-cell bacteria and archaea against invading viruses, naturally occurring CRISPR uses 2 main components. The first are short snippets of repetitive DNA sequences called clustered, regularly interspaced short palindromic repeats, or simply CRISPRs. The second are Cas, or CRISPR-associated proteins, which chop up DNA like molecular scissors. When a virus invades a bacterium, Cas proteins cut out a segment of the viral DNA to stitch into the bacterium's CRISPR region, capturing a chemical snapshot of the infection. Those viral codes are then copied into short pieces of RNA. This molecule plays many roles in our cells. But in the case of CRISPR, RNA binds to a special protein called Cas9. The resulting complexes act like scouts, latching onto free-floating genetic material and searching for a match to the virus. If the virus invades again, the scout complex recognizes it immediately, and Cas9 swiftly destroys the viral DNA. Lots of bacteria have this type of defense mechanism, but in 2012, scientists figured out how to hijack CRISPR to target not just viral DNA, but any DNA in almost any organism. With the right tools, this viral immune system becomes a precise gene editing tool, which can alter DNA and change specific genes almost as easily as fixing a typo. Here's how it works in the lab. Scientists design a guide RNA to match the gene they want to edit and attach it to Cas9. Like the viral RNA in the CRISPR immune system, the guide RNA directs Cas9 to the target gene, and the protein's molecular scissors snip the DNA. This is the key to CRISPR's power. Just by injecting Cas9 bound to a short piece of custom guide RNA, scientists can edit practically any gene in the genome. Once the DNA is cut, the cell will try to repair it. Typically, proteins called nucleases trim the broken ends and join them back together. But this type of repair process, called non-homologous end joining, is prone to mistakes and can lead to extra or missing bases. The resulting gene is often unusable and turned off. However, if scientists add a separate sequence of template DNA to their CRISPR cocktail, cellular proteins can perform a different DNA repair process called homology-directed repair. This template DNA is used as a blueprint to guide the rebuilding process, repairing a defective gene, or even inserting a completely new one. The ability to fix DNA errors means that CRISPR could potentially create new treatments for diseases linked to specific genetic errors, like cystic fibrosis or sickle cell anemia. And since it's not limited to humans, the applications are almost endless. CRISPR could create plants that yield larger fruit, mosquitoes that can't transmit malaria, or even reprogram drug-resistant cancer cells. It's also a powerful tool for studying the genome, allowing scientists to watch what happens when genes are turned off or changed within an organism. CRISPR isn't perfect yet. It doesn't always make just the intended changes. And since it's difficult to predict the long-term implications of a CRISPR edit, this technology raises big ethical questions. It's up to us to decide the best course forward as CRISPR leaves single-celled organisms behind and heads into labs, farms, hospitals, and organisms around the world. Wrap your head around the implications of CRISPR with this playlist on genetics,
So hopefully that answered your question, but I think ultimately at the end of the day, I think the best way to probably describe it is we decide what gene we want to change, we make an RNA that matches that gene, and then Cas9 follows the RNA. And then when the RNA finds its match, Cas9 cuts. Is this, hopefully this answers the question. We tell Cas9 this is your target and this is yes. Can CRISPR be weaponized? That's actually part of the discussion I have also with ethical problems, the ethical limitations and ethics behind this. Speaking of Q, that's something that we're next going to discuss. Hopefully I've answered everything that we needed for what CRISPR is, how it works. But I'm going to go into now the limitations it has and ethics, okay? So at this point, we can all see how pretty incredible and powerful this tool is. Short comedy, yeah. Sorry. I hope I'm doing an okay job answering your guys' questions or helping. I feel bad when I can't answer the questions or if like I'm not explaining it well enough. Oh, did I oopsie. Did I actually? Whoopsie. My bad. Whoopsie. I did this at like 2:30 in the morning, by the way. I stayed up late doing this. 10 out of 10. Unwatchable. Can't watch anymore, guys. Can't watch. There you go. All right. Anyway. That being said, or the scientist equivalent. I never claimed to be a scientist, so joke's on you guys. All right. Okay. Big things. So at this point, like I mentioned, it sounds really cool, really powerful, but it's important to talk about the limitations it has and the ethical questions it raises. So as Q mentioned, it can bring a lot of problems potentially in the future, which I have another video which will kind of go into a little bit more detail. Because CRISPR isn't magic, and more importantly, science has limitations, there are a lot of problems that can arise with CRISPR. One of the major limitations is accuracy. So CRISPR is designed to cut DNA at a very specific spot, but sometimes it cuts in places where it's not intended. I need someone to share their notes with me. I'm late for class. She's late. M's a smart noodle. I'm sure M could figure it out and do pretty well on the quiz. But welcome in, Em. I hope you're doing good. I hope you had a lovely afternoon. What was I saying? Oh, basically, sometimes it cuts in places where it doesn't intend to. So obviously, that's not great. These are called off-target effects, and they can potentially cause unwanted changes elsewhere in the genome. Things that we didn't intend to happen, okay? Things that we didn't expect. And another challenge is delivery. Getting CRISPR into the right cells in the right amount at the right time is harder than it sounds, especially in complex organisms like humans. There's also the issue of efficiency. Not every cell gets edited, and not every edit works the way we want it to. So some edits partially work, and others fail completely. So there's the reality that we still don't fully understand every single gene. So even if we edit a gene successfully, predicting all of the long-term effects isn't always possible yet. So that's some of the big problems and limitations we have for CRISPR. Yes, it's really cool, but there is still a lot that we don't know. And I think that's the kind of, it's the beauty of science, but also the scary part of science. And scary part of CRISPR is that you can start messing around with genes all you want, but who's to say you're not messing with something, or it turns out it's great now, but who's to say it doesn't hurt it later down the line or make things bad down the line, especially in humans, right? Okay. Now, the limitations of CRISPR aren't just technical. Some of the biggest questions that we do have are ethical. So, ethical concerns, when one of the big ones would be a major debate involving human genome editing, especially when it comes to embryos. If DNA is edited in an embryo, those changes don't just affect one person, they can also be passed down to future generations. So that raises a really big question of who, like, we have like designer babies, right, for one. And it also brings big questions of who gets to decide what should be edited and what counts as treating a disease versus enhancing a trait. So like, oh, I want my kid to be X tall. I want them to have blue eyes and blonde hair. Well, those are traits, but also it's like, this isn't what we want or what we need for CRISPR to be. You know, it's like, at what point do we draw the line and say we need to stop and go back to, hey, this could stop like sickle cell anemia, stuff like that, and say, you know, this is for this specifically. So who gets to determine that? But there's a difference between fixing a life-threatening mutation and choosing traits like I mentioned, eye color or hair or height, you know. But Build-A-Bear for babies is true. That's the thing. It's like we're basically playing Build-A-Bear for babies. In the world of Bella, this ain't built. I mean, you're not wrong. It's true. The other thing that it could potentially raise is equity and access. The big concern is access. If genome editing becomes part of medicine, who gets access to it? Will it be available to everyone, or is it just those who can afford it? There's a real big concern that genetic technologies can, you know, could potentially increase social inequality if they're not handled responsibly. And it's, you know, we're playing designer DNA, right? So you know, like I mentioned, we all know the term, or we've heard the term designer babies. It refers to the idea of selecting or editing traits before birth. If the technology allows it, many scientists and ethicists agree that this crosses an important ethical line. But again, it's like, what's stopping us, right? Just because we can change DNA doesn't mean every change should be made. That being said, there's also environmental and ecological risks that come into play. CRISPR isn't just used in humans. It's also used in plants, animals, and microorganisms. Editing genomes in the wild could have unintended consequences to our ecosystems. So once a genetic change is released into nature, it can be very difficult, if not impossible, to reverse it. A certain rich guy keeps editing his babies to be all boys and disown them because what? That's insane, huh? At what point does CRISPR go from life-saving research to playing God? Like, exactly. And that's the thing. That's a lot of the problems that CRISPR, or I guess the ethical concerns that CRISPR has brought up, is that people are like, where does the line drawn? That's scary. And it's like, who gets to draw that line? Do we have discussions? Where does it end, basically? I think the biggest thing is that it requires strict regulation and oversight. And that's what they do today. So this is why research, of course, is heavily regulated, right? Scientists don't just ask, can we do this? A lot of the time it's a, should we do this? And so that's something that, like, is very big, of like, it's, you start to cross a line and then it's like, all right, it's no longer about can we, it's like, should we? Ethical oversight, regulations, and public discussion are really critical as this technology develops. And again, like, where we're at now and versus where we'll be in the future, insanely different, like night and day, I bet. Like, I can't imagine where this is going to go. But CRISPR has the potential to do enormous good, from treating genetic diseases to advancing research, but it also carries real risks of, you know, and serious ethical questions. The goal isn't to stop progress, it's just to guide it responsibly. And because when you're editing the code of life, caution matters just as much as curiosity. And I think that's the biggest takeaway here when it comes to CRISPR. Okay. Insert Jurassic Park quote here. Exactly. That, I think that's like the biggest thing, is that we're back to the concept of Jurassic Park. Doesn't mean that we should, even though we can, you know? Okay. Okay. All right. That being said, I do have another video to show you guys. I think that this one it's a little longer. The last two videos I have are fairly a little bit longer, but I think that they're very, very interesting. And I think that, so this one's going to be about genetic engineering will change everything forever and CRISPR. And then the last one is a real world application. But I'll talk a little bit more about real world applications before we jump in. Okay. Sci-fi series called The Sleepless Trilogy that did explore what happens on a political and social level when you create super people. Like, it's slippery slope towards, yeah, it's insane. Okay, are you guys ready? Mother Nature always finds a way. Always finds a way, guys. Okay. All right. I think that this is a really cool video, and it brings up some very interesting concepts, very interesting stuff that plays into CRISPR, and I hope you guys like the video. I'm gonna, of course, turn off my camera, and then we'll watch the video, and then we can discuss a little bit afterwards. Okay? Ugh. Hold up. I need to stand up, so don't mind me if you hear my chair, but I'm gonna stand up while we play this.
Imagine you were alive back in the 1980s and were told that computers would soon take over everything, from shopping to dating and the stock market. That billions of people would be connected via a kind of web. That you would own a handheld device orders of magnitude more powerful than supercomputers. It would seem absurd, but then all of it happened. Science fiction became our reality, and we don't even think about it. We're at a similar point today with genetic engineering. So let's talk about it. Where it came from, what we're doing right now, and about a recent breakthrough that will change how we live and what we perceive as normal forever. Humans have been engineering life for thousands of years. Through selective breeding, we strengthened useful traits in plants and animals. We became very good at this, but never truly understood how it worked, until we discovered the code of life, deoxyribonucleic acid, DNA, a complex molecule that guides the growth, development, function, and reproduction of everything alive. Information is encoded in the structure of the molecule. 4 nucleotides are paired and make up a code that carries instructions. Change the instructions and you change the being carrying it. As soon as DNA was discovered, people tried to tinker with it. In the 1960s, scientists bombarded plants with radiation to cause random mutations in the genetic code. The idea was to get a useful plant variation by pure chance. Sometimes it actually worked too. In the 70s, scientists inserted DNA snippets into bacteria, plants, and animals to study and modify them, for research, medicine, agriculture, and for fun. The earliest genetically modified animal was born in 1974, making mice a standard tool for research, saving millions of lives. In the 80s, we got commercial. The first patent was given for a microbe engineered to absorb oil. Today, we produce many chemicals by means of engineered life, like life-saving clotting factors, growth hormones, and insulin, all things we had to harvest from the organs of animals before that. The first food modified in the lab went on sale in 1994, the Flavor Saver tomato, a tomato given a much longer shelf life via an extra gene that suppressed the buildup of a rotting enzyme. But GM food and the controversy surrounding them deserve a video of their own. In the 1990s, there was also a brief foray into human engineering. To treat maternal infertility, babies were made that carried genetic information from 3 humans, making them the first humans ever to have 3 genetic parents. Today, there are super-muscled pigs, fast-growing salmon, featherless chickens, and see-through frogs. On the fun side, we made things glow in the dark. Fluorescent zebrafish are available for as little as $10. All of this is already very impressive, but until recently, gene editing was extremely expensive, complicated, and took a long time to do. This has now changed with a revolutionary new technology now entering the stage: CRISPR. Overnight, the costs of engineering have shrunk by 99%. Instead of a year, it takes a few weeks to conduct experiments, and basically everybody with a lab can do it. It's hard to get across how big a technical revolution CRISPR is. It literally has the potential to change humanity forever. Why did this sudden revolution happen, and how does it work? Bacteria and viruses have been fighting since the dawn of life. So-called bacteriophages or phages hunt bacteria. In the ocean, phages kill 40% of them every single day. Phages do this by inserting their own genetic code into the bacteria and taking them over to use them as factories. The bacteria try to resist, but fail most of the time because their protection tools are too weak. But sometimes bacteria survive an attack. Only if they do so can they activate their most effective antivirus system. They save a part of the virus DNA in their own genetic code in a DNA archive called CRISPR. Here, it's stored safely until it's needed. When the virus attacks again, the bacterium quickly makes an RNA copy from the DNA archive and arms a secret weapon, a protein called Cas9. The protein now scans the bacterium's insides for signs of the virus invader by comparing every bit of DNA it finds to the sample from the archive. When it finds a 100% perfect match, it's activated and cuts out the virus DNA, making it useless, protecting the bacterium against the attack. What's special is that Cas9 is very precise, almost like a DNA surgeon. The revolution began when scientists figured out that the CRISPR system is programmable. You can just give it a copy of DNA you want to modify and put the system into a living cell. If the old techniques of genetic manipulation were like a map, CRISPR is like a GPS system. Aside from being precise, cheap and easy, CRISPR offers the ability to edit live cells, to switch genes on and off, and target and study particular DNA sequences. It also works for every type of cell, microorganisms, plants, animals or humans. But despite the revolution CRISPR is for science, it's still just a first-generation tool. More precise tools are already being created and used as we speak. In 2015, scientists used CRISPR to cut the HIV virus out of living cells from patients in the lab, proving that it was possible. Only about a year later, they carried out a larger-scale project with rats that had the HIV virus in basically all of their body cells. By simply injecting CRISPR into the rats' tails, they were able to remove more than 50% of the virus from cells all over the body. In a few decades, a CRISPR therapy might cure HIV. And other retroviruses, viruses that hide inside human DNA like herpes, could be eradicated this way. CRISPR could also defeat one of our worst enemies, cancer. Cancer occurs when cells refuse to die and keep multiplying while concealing themselves from the immune system. CRISPR gives us the means to edit your immune cells and make them better cancer hunters. Getting rid of cancer might eventually mean getting just a couple of injections of a few thousand of your own cells that have been engineered in the lab to heal you for good. The first clinical trial for a CRISPR cancer treatment on human patients was approved in early 2016 in the US. Not even a month later, Chinese scientists announced that they would treat lung cancer patients with immune cells modified with CRISPR in August 2016. Things are picking up pace quickly. And then there are genetic diseases. There are thousands of them, and they range from mildly annoying to deadly or entail decades of suffering. With a powerful tool like CRISPR, we may be able to end this. Over 3,000 genetic diseases are caused by a single incorrect letter in your DNA. We are already building a modified version of Cas9 that is made to change just a single letter, fixing the disease in the cell. In a decade or two, we could possibly cure thousands of diseases forever. But all of these medical applications have one thing in common. They are limited to the individual and die with them, except if you use them on reproductive cells or very early embryos. But CRISPR can and probably will be used for much more: the creation of modified humans, designer babies, and will mean gradual but irreversible changes to the human gene pool. The means to edit the genome of a human embryo already exist, though the technology is still in its early stages, but it has already been attempted twice. In 2015 and 2016, Chinese scientists experimented with human embryos and were partially successful on their second attempt. They showed the enormous challenges we still face in gene editing embryos, but also that scientists are working on solving them. This is like the computer in the 70s. There will be better computers. Regardless of your personal take on genetic engineering, it will affect you. Modified humans could alter the genome of our entire species because their engineered traits will be passed on to their children and could spread over generations, slowly modifying the whole gene pool of humanity. It will start slowly. The first designer babies will not be overly designed. It's most likely that they will be created to eliminate a deadly genetic disease running in a family. As the technology progresses and gets more refined, more and more people may argue that not using genetic modification is unethical because it condemns children to preventable suffering and death and denies them the cure. But as soon as the first engineered kid is born, a door is opened that can't be closed anymore. Early on, vanity traits will mostly be left alone. But as genetic modification becomes more accepted and our knowledge of our genetic code enhances, the temptation will grow. If you make your offspring immune to Alzheimer, why not also give them an enhanced metabolism? Why not throw in perfect eyesight? How about height or muscular structure? Full hair? How about giving your child the gift of extraordinary intelligence? Huge changes are made as a result of the personal decisions of millions of individuals that accumulate. This is a slippery slope. Modified humans could become the new standard. But as engineering becomes more normal and our knowledge improves, we could solve the single biggest mortality risk factor, aging. 2/3 of the 150,000 people who die today will die of age-related causes. Currently, we think aging is caused by the accumulation of damage to our cells, like DNA breaks and the systems responsible for fixing those wearing off over time. But there are also genes that directly affect aging. A combination of genetic engineering and other therapy could stop or slow down aging, maybe even reverse it. We know from nature that there are animals immune to aging. Maybe we could even borrow a few genes for ourselves. Some scientists even think biological aging could be something that eventually just stops being a thing. We would still die at some point, but instead of doing so in hospitals at age 90, we might be able to spend a few thousand years with our loved ones. Research into this is in its infancy, and many scientists are rightly skeptical about the end of aging. The challenges are enormous, and maybe it is unachievable. But it is conceivable that people alive today might be the first to profit from effective anti-aging therapy. All we might need is for someone to convince a smart billionaire to make it their next problem to solve. On a bigger scale, we certainly could solve many problems by having a modified population. Engineered humans might be better equipped to cope with high-energy food, eliminating many diseases of civilization like obesity. In possession of a modified immune system, with a library of potential threats, we might become immune to most diseases that haunt us today. Even further into the future, we could engineer humans to be equipped for extended space travel and to cope with different conditions on other planets, which would be extremely helpful in keeping us alive in our hostile universe. Still, a few major challenges await us, some technological, some ethical. Many of you watching will feel uncomfortable and fear that we will create a world in which we will reject non-perfect humans and pre-select features and qualities based on our idea of what's healthy. The thing is, we are already living in this world. Tests for dozens of genetic diseases or complications have become standard for pregnant women in much of the world. Often, the mere suspicion of a genetic defect can lead to the end of a pregnancy. Take Down syndrome, for example, one of the most common genetic defects. In Europe, about 92% of all pregnancies where it's detected are terminated. The decision to terminate a pregnancy is incredibly personal, but it's important to acknowledge the reality that we are pre-selecting humans based on medical conditions. There is also no use in pretending this will change, so we have to act carefully and respectfully as we advance the technology and can make more and more selections. But none of this will happen soon. As powerful as CRISPR is, and it is, it's not infallible yet. Wrong edits still happen, as well as unknown errors that can occur anywhere in the DNA and might go unnoticed. The gene edit might achieve the desired result, disabling a disease, but also might accidentally trigger unwanted changes. We just don't know enough yet about the complex interplay of our genes to avoid unpredictable consequences. Working on accuracy and monitoring methods is a major concern as the first human trials begin. And since we've discussed a possible positive future, there are darker visions too. Imagine what a state like North Korea could do if they embraced genetic engineering. Could a state cement its rule forever by forcing gene editing on their subjects? What would stop a totalitarian regime from engineering an army of modified super soldiers? It is doable in theory. Scenarios like this one are far, far off into the future, if they ever become possible at all. But the basic proof of concept for genetic engineering like this already exists today. The technology really is that powerful. While this might be a tempting reason to ban genetic editing and related research, that would certainly be a mistake. Banning human genetic engineering would only lead to the science wandering off to a place with jurisdiction and rules that we're uncomfortable with. Only by participating can we make sure that further research is guided by caution, reason, oversight, and transparency. Do you feel uncomfortable now? Most of us have something wrong with them. In the future that lies ahead of us, would we have been allowed to exist? The technology is certainly a bit scary, but we have a lot to gain, and genetic engineering might just be a step in the natural evolution of intelligent species in the universe. We might end disease. We could extend our life expectancy by centuries and travel to the stars. There's no need to think small when it comes to this topic. Whatever your opinion on genetic engineering, the future is approaching no matter what. What has been insane science fiction is about to become our new reality, a reality full of opportunities and challenges. Videos like this would not be possible without viewer donations on...
Okay. I think that's a really, interesting video. It brings a lot of questions up. It brings a lot. Yeah, I think that one's, super, super interesting to talk about. But yeah, no, I was reading a lot of your guys' messages, and it's just absolutely bonkers to think about, things like this. I know that I was actually kind of hesitant because I didn't want to, bring anything politics up, but it is something that, people do wonder about, and if it's something that potentially could happen in the future, if, who's to say we don't make super soldiers or stuff like that. Who wants a designer baby? No. Now that we watched it, does anybody want a designer baby? But no, it does. It's very interesting. Also, Blair, welcome in. I'm sorry I didn't say hello when you first popped in. I was busy. I was busy letting the thingy go, but I hope you're doing well. We're just talking about CRISPR, and we're talking about genome editing, and we've already kind of done the groundwork. We're already kind of we've talked about CRISPR, talked about the limitations and its ethics, and now we're going to talk about real world application. And then we'll close, and then we'll talk about Kahoot questions, and we'll do our little quiz, and maybe somebody will win, and you could win a prize. It'll be fun. I want a Gucci baby. Ethics are always essential to discuss regarding humans. Exactly. I think that's the big thing is, at the end of the day, I think it is an important thing to talk about, is because science brings up a lot of hypothetical questions, but also it can get very ethical at the same time. Unfortunately, it does sometimes get political, and I wish that it wasn't that situation, but it's the unfortunate reality. Next, I'm going to talk about a little bit more about real world applications and how CRISPR can be beneficial and how we can utilize CRISPR. And then we can watch another video, and then we'll close. Designer babies don't have birthmarks. They have brand logos. Just a little brand mark. It's fine. Just get some Gucci babies. It's okay. But as you guys already kind of know, and 11 sponsored my baby, get out. CRISPR's already being used in the real world, and it's being used in some really crazy ways, amazing ways, and I just want to kind of talk about things that it's being used for. So the food industry, we've been using it for the food industry. CRISPR can make food safer and more nutritious. Creating fruits and vegetables that are resistant to disease, last longer, or have more vitamins. That's a way that we can apply it to the food industry. My baby was born with a Walmart logo. Oh no. Blind box my designer baby. It's just normal baby making. Yeah, exactly. Another way that we can, utilize CRISPR is through livestock improvement. CRISPR can help breeders create healthier animals. For example, pig resistant to certain viruses, or cows that produce more milk without health problems. And again, this is another ethical concern of like us, quote unquote, playing the role of God, right? Then, of course, we have plant biotechnology. Scientists can improve crops quickly. An example of this would be like plants that tolerate drought, resist pests, or, have better yields. Another thing that CRISPR can be utilized for is biofuels. CRISPR can enhance microbes or plants that make biofuels. An example of this would be like modifying algae or yeast to produce energy sources more efficiently. We end up with 50-foot tall cows to increase beef production. That'll be wild. Crop sterile, so farmers need to buy more seed from my employer, increasing the odds of my receiving a thick yearly bonus. I mean, figure it out, Q. Do it from your place. They might go to somebody else, but could do it, maybe, theoretically. Also, the correction of genetic and metabolic diseases. I think this is the main one that we talk about mostly when you think about CRISPR, but it can fix faulty genes in humans. An example of this would be treating like inherited diseases like sickle cell anemia or certain metabolic disorders. It's also utilized for drug discovery or development in screens. CRISPR helps scientists study diseases faster and find new drugs. So an example of this would be editing cells to test how drugs affect specific genes, speeding up research. And then, of course, here, the control of bacterial and viral diseases. And this is another one that we've kind of already talked about, but CRISPR can target harmful bacteria or viruses directly. An example of this would be, like developing therapies to fight antibiotic-resistant bacteria or prevent viral infections in crops or in animals, stuff like that. So, it's just kind of like how it could treat things like this, like how it's applicable to our real world. Generally, farmers would use the seeds they reap, but designer crops are infertile. Yeah, the ethical board for human genetics would be wild. I bet you it goes crazy. I wonder if it could help. I mean, I don't, like, the possibilities for stuff like this could be endless. But again, it's like, what we know is like this much. CRISPR's worlds of what we don't know, insane. Wild. And I think that's the, like, really, that's the beauty of it. And it's also, like, how scary it is at the same time. Because there's so much there that we don't know. When I talked about like sickle cell anemia, researchers can edit the faulty gene in patient cells, then reintroduce them to the body to make healthy blood cells. I think that's insane. That's like revolutionary, right? Like with certain types of cancer, CRISPR helps scientists understand which genes are driving tumor growth, opening up new treatment possibilities. It's wild, the like different areas or routes that we could take this tools to like into, but it's also, I don't know, it's hard to believe. And like, I can't even imagine where we'll be in the future with this. Live 1,000 years, but if my brain is still gonna go after 100 years, I don't know if I want that. And that's the other thing. It's another one of those like, maybe we can, but does it mean we should? Maybe there's some billionaires out there who are going to be like, hey, I really want to fund this. Let's fund it. What's the line in mental health? Because I definitely need a medication to manage my ADHD. I don't even know, like, if it's been explored yet for CRISPR managing neurological, like, anything neurological or like, anything genetically I mean, there's a lot of genetic disorders or you know, diseases out there that could be treated with this, but like, I don't know if they've even looked into like ADHD or stuff like that. A bloodline of someone who with edited genes will go. See, that's the other thing. It's like, once we start editing people, how is that going to affect our gene pool? Like, as humans, how is it going to affect the human genome in generations to come? And we don't even know the long-term effects of all of that. Like, who's to say right now it's all great and dandy. Our designer babies are all cool and neat, and they're athletes, they're smart, they have, you know, no problems, they're uber healthy. But what does that have long-term effects for generations later? Is that also going to be the case, or is something bad going to happen later on? Who's to say? Can we use CRISPR then? Or things like that later on down the line to help those generations? Or is it going to be a problem? Really don't know what repercussions would be down the line. Exactly. You know exactly what I'm talking about. How can I personally profit from CRISPR? Get into this ish. I'm sure there's a lot of money. Baby, design a baby, push them to play football, get them into good college. You know what? There you go. Get your designer baby. They could probably do it. Likely, the likelihood of a CRISPR gene having a mutation. So that's the other thing. CRISPR has its like limitations. Who's to say it even works? You know, it does a fairly good job at being precise, but like I mentioned, it's like we don't know. It sometimes messes up. So you could technically be, you know, working towards that designer baby, and it doesn't turn out how you expected it to be because CRISPR didn't quite do what it needed to do. Could be mutations down the line with all the mixing if it were to happen. Yeah, exactly. We might be looking at things that potentially could affect future generations. CRISPR, the edits that you're making with CRISPR is what could affect future generations. It's not that like CRISPR in general is the problem affecting like future generations. It's like what we're doing with CRISPR is what could affect future generations. Not CRISPR like directly, it's what we're doing with it. That could be the problem. So that's where we're getting like our designer babies. Okay, that's, you know, could this gene actually make it a problem in the future? It's the tool. Wrong edit, suddenly humanity goes 3 branches down the animal kingdom. Who knows? I don't know. It's hard to say, and we know so little. I mean, we know a lot right now. It's insane to think of like how much we've learned, but again, it's like, it's wild to think of where it can potentially go in the future. You need generations of CRISPR babies to know the full extent of how it affect humans. And that's the thing, we won't know until that time comes, and it's sad, but it's the reality of it. But yeah, can you imagine the heyday Darwin would have knowing about CRISPR? It's insane. Like, so many. Can you imagine all of the scientists of the past like knowing something about this? Oh, I bet you they'd have like an aneurysm. Like, there's no way. That's insane. Oh my gosh, Kaneki, thank you so much for the raid. Welcome in, raiders. Hello. I'm so sorry. I have all of my alerts turned off right now, specifically because we're doing a science stream and we're talking about CRISPR and genome editing. We're nearing the end, but we are going to be doing a wrap-up video where we discuss, you know, some of the stuff. But thank you so much for being here. Thank you for popping in. It really does mean a lot to me that you would pop in during a science stream. Hello, Saw, it looks super cool. Well, thank you so much for the raid. Thank you, everybody. Those of you just popping in that don't know me, my name is Miss Spooky, also known as Spooky. I do cozy games Mondays, horror games Wednesdays, and Fridays are multiplayer days. I personally
You're my friends now. We're having
thank you so much for the follow. My follows are anonymous. I've now switched over so that I'm not calling people out of lurks or anything. But thank you again for trusting me with your community. Thank you for being here. I typically don't do science streams, but I have a background in microbiology with a minor in chemistry, and sometimes we do science streams every now and then. Typically, I've done it where I do science analysis of like The Last of Us, or I've done World War Z, or I've done Mythbusters, and this time we actually turned it into like a mini lecture lecture where we talk about, do like a crash course of genome editing and CRISPR. And it's barely scratching the surface of what CRISPR has to offer, but it does create really good conversation, and that's something that we've been discussing, and it's been a really, really good stream, honestly. It's been really fun. I really liked the science streams. I'm planning on trying to do a little bit more this year. I have a goal of hitting 4 science streams this year, so this counts as one of them. So I'm going to try to do at least 3 more science streams this year. What those are going to be on, I usually leave that up to the Discord and the chat to decide. But if you are interested, my bot's off, so I completely forgot my bot is completely turned off. But I typically have my thing. Hold on, let me. Can I get a mod who can put the Discord thing in the chat, please? Thank you. But thank you again for trusting me with your community. Thank you for being here. I hope you had a lovely stream, honestly, truthfully. But hold on, I would like to know what you guys were up to while we're kind of just chatting and wrapping up towards the end. And we're gonna be having a quiz for those who stuck around and who are in here. There it is. Thank you. There's the Discord if you are interested in joining. No pressure at all. I know that many streamers and many people are part of several thousand Discords. So I do keep up with my schedule there. I do put polls there for, to get your guys' opinions and stuff like that, just for content and for things that we'd like to do on stream, things that we would think would be fun. But welcome in, Landpage, and welcome in, Kanagi, again. I really do appreciate it. That's the main issue, because who's to say we'd even be successful enough to have potentially a pure CRISPR baby? Then in between is what it's the risk, since it's vastly unknown and we can't predict every possible outcome. That's the crazy part. We're just talking about how the ethical concerns of CRISPR and what it has to offer. CRISPR is an amazing, crazy tool. If you are familiar with genome editing, it is a way to accomplish that. We're just talking about some of the issues that could potentially arise with genome editing like CRISPR, but I just talked about some of the real world applications of how this can be utilized. The thing is, I do have a video that I think is really cool. It happened not too long ago. I believe the video is from last year. It's from Hank Green, actually. And he talks about one of the ways that CRISPR has been utilized and how it's helped a family. And I'll show you guys that here in a few moments. Start making designer cats with CRISPR. Like, I want a tiger, but how's cat size? Exactly. That's what I want. But it's crazy to think about that, like, who's to say we don't release something like, that's CRISPR edited like a cat into the wilds, and then it starts breeding out in the wilds. What's going to happen later? You know what I'm saying? Is that what people use for GMO crops? So it can be. We can use it for, here, let me go to the screen real quick. We can use it for a lot of different areas. I've mentioned we can use it for food industry. CRISPR can make it safer for food, food safer and more nutritious. It can be, used to make plants or fruits that resist disease last longer, or maybe add more vitamins to the products or the crops. It could be for livestock, maybe preventing, help breeders create healthier animals. It could be for scientists, to improve crop yields. It can be used for biofuels, enhancing microbes or plants that make biofuels. It could be used for correction of metabolic genetics or, diseases, stuff like that. It can fix faulty genes in humans. It can be for drug discovery, development, and, like screens. So, it can help us study disease faster and find newer drugs. It can also, control bacterial and viral diseases. So, can target harmful bacteria or viruses directly, stuff like that. So there's a lot that CRISPR can do. And I think the biggest takeaway is like, there's a lot we can do with it, but where do we stop? When can we, when is it not okay to keep going? Scratch his chin. Bigger D. God dang it, Steve. Stop making my discoveries weird. Exactly. My sister used to used to use my hairless cat in her genetics presentation when she taught high school. Oh, that's really cute. There's a lot we can do with it, but a lot we shouldn't do with it. Exactly. And I think that's the biggest takeaway about this. I do have one more video that I'd like to show you guys before we kind of wrap up and we move to the quiz portion of, you know, whether or not you guys were able to stay on task, stay focused. The winner of the little quiz, and it's a Kahoot. Whoever's the fastest gets higher points. Whoever wins will get a little prize at the end. I just ask that people keep their whispers open. The thing I have with this is that Kahoot's a little funky. I had to get like a weird version of Kahoot. They've put paywalls behind Kahoot for whatever reason. I think it was probably because of COVID times. Not sure, unconfirmed. That's what I believe. But I'll kind of go into that a little bit more when we get there. But I do have one last video for this, and it's a real world application. Shout out to Hank Green for putting this video together, because I think it's really, really good. The one nice part about Kahoot is that nobody needs to purchase anything. You could just you basically just use the QR code that'll pop up on the screen, or you type it in on your phone on Google. And but yeah, we'll take a break. We can take a little break after we finish this video, and then we'll get in to do some little Kahoot stuff. Okay, all right. So this is the last video I'll be showing, and then I'll kind of, while I'm closing, just kind of put some final remarks that I have to say, and then we'll take a little break, and then we'll get into the questions. Okay, all right. Will the last video be on the quiz? No, I don't believe it is. It is not on the quiz. What should we call you? Miss Spooky or Miss Pookie? Miss Spooky, thank you. Mistress Spooky, thanks.
It's August of 2020.
Fudge. Miss Spooky Dookie, thank you. All right. All right, guys. I'm going to show you guys this last video, and I'll be quiet, and then our boy here will tell you what happened, okay?
It's August of 2024, and a beautiful newborn baby in Philadelphia has just been diagnosed with a rare liver disease. Caused by a genetic mutation, this disease is incredibly deadly, killing around half of its patients in infancy. And the only cure is a liver transplant, something this baby, nicknamed KJ, is too little to get. A team of scientists has a more ambitious plan. They are racing against the clock to edit KJ's DNA inside of his own body, something that has never been achieved before. Spoiler alert, they did it. At time of filming, KJ is doing great thanks to a treatment so advanced it sounded to his own parents like science fiction. But it is a reality now, thanks to these scientists, and they hope that KJ will be the first of many to benefit. Here is how they did it. Now, KJ is not the first person ever to receive gene editing therapy, far from it. Various approaches have been developed over the last few decades for more common diseases. The history of gene editing in humans has also involved multiple ongoing ethical and technical challenges. But KJ was the first to receive a personalized in vivo gene editing drug. In vivo means inside a living thing, as opposed to in vitro, which means in a test tube or a petri dish, or insert lab paraphernalia here, meaning previously gene editing in humans was largely done by removing their cells, treating them, and putting them back into the body. And personalized, in this case, means the therapy was tailor-made just for little KJ. In other words, the research team engineered a microscopic fleet of custom gene editors to travel via IV infusion to the liver and literally modify the DNA inside the cells. The idea is that this modification would correct a catastrophic typo in KJ's DNA. KJ's father has been quoted as saying that the scientist's explanation sounded like a futuristic sci-fi out-of-this-world technology that he did not know anything about. But who would know about this? Just the doctors who are doing it. It's new. What he did know, though, was that KJ's life almost certainly depended on it. Helping this baby has been an amazing feat that offers hope that he will have a long, healthy life. But even better, it could also pave the way to treat all kinds of other often fatal and, crucially, super rare diseases. So let's get into saving KJ play-by-play. Shortly after he was born, doctors diagnosed KJ with carbamoyl phosphate synthetase 1, or CPS1 deficiency. Researchers at the University of Pennsylvania and Children's Hospital of Pennsylvania sprang into action immediately. They had used similar approaches to try to help children in similar cases, but they had learned valuable lessons, allowing them to complete the process faster than before. They were hoping beyond hope that KJ would be the lucky first. The team knew that every day would be crucial and that they would have to execute their plan to perfection. But first, let's get into the details of this diagnosis. That CPS1 gene codes for an important liver enzyme. KJ received a faulty version from each of his parents. KJ and others with CPS1 deficiency have a misspelling in the DNA sequence of the gene. This enzyme is involved in the first of 5 crucial steps in what's called the urea cycle. This is a series of biochemical reactions that convert waste ammonia in the blood into urea, allowing it to be excreted when you pee. There are other urea cycle disorders in which another of the 5 steps is disrupted by a different gene mutation. This misspelling causes the liver cells to produce a broken enzyme. All humans produce a small amount of ammonia, mostly as a byproduct of protein metabolism. In patients with CPS1 deficiency, ammonia builds up in the brain when they consume protein. KJ had to start a grueling regimen immediately after birth, including taking an intensive amount of drugs. He also had to eat a restricted amount of protein in his diet just to stay alive. And this is bad for a baby. Babies need protein. The only cure for this disease is a liver transplant, but CPS1 deficiency is so dangerous that not all patients survive long enough to get one. That's because there are a lot of risks and challenges to giving liver transplants to tiny infants. One of those challenges is that they're just not big enough. KJ's disorder is considered ultra rare. It's one of thousands of different so-called rare diseases, each of which occurs in very, very few people, and most of which are caused by a genetic error. But if you add all of these rare diseases together, millions of people have one of those diseases. CPS1 deficiency is thought to affect fewer than 1 in a million people. To be born with such an improbable mutation is largely a result of bad luck, but KJ's parents, doctors, and personalized research team would do everything in their power to defy the likely death sentence. The clock started ticking right when he was born, and the tenacious researchers were ready to move. Right away, they identified a specific CPS1 problem variant in KJ's DNA called Q335X, which came from the child's father. This specific variant causes liver cells to create a shortened version of the CPS1 enzyme. However, if KJ only had that one mutation, he would have been okay. CPS1 deficiency is a recessive disease and requires both versions of the gene to be non-functional. And the team found that the copy of the CPS1 protein from the baby's mom, E714X, also leads to a shortened protein. But Q335X had been associated with CPS1 deficiency in another newborn, so that was the one they chose to target. The plan also involved creating what's called a patient-specific cell line, which is a collection of cells with someone's unique genetic sequence that can be studied. It wasn't safe enough to biopsy KJ's liver cells, though. Instead, the scientists synthesized and inserted specific DNA sequences from KJ's genome into a different cell line, one that's been grown and used in research since 1982. The cells were ready to go by the time KJ was 1 month old. Meanwhile, they also had to create a therapy customized to correct the specific mutation in KJ's liver cells, but they were on top of that too. CRISPR-Cas9 technology is the world's best known type of gene editor. The CRISPR component borrows bacterial machinery to find a specific DNA sequence. Cas9 is an editor protein involved in snipping and changing that sequence. KJ's treatment is similar to CRISPR-Cas9, but uses a different sequence finder and editor. One piece of KJ's treatment, the guide RNA, was engineered to find the right spot on chromosome 2 where the mutation was located. Attached to that guide RNA would be an adenine base editor, which is a protein that edits the DNA strand at a specific site. This editor rewrites only one letter, replacing an A, one of the ATGC DNA alphabet, with a G. For this reason, base editors like this one come come with a much smaller risk of unintended consequences than traditional CRISPR-Cas9. The ultimate objective is for this small edit to prompt the cell to fix the faulty gene so it starts to produce the CPS1 enzyme. The team had this treatment formulated by the time the baby was 2 months old. They dubbed this bespoke treatment K-ABE in reference to KJ and the name of the editor. It would then be encapsulated into extremely tiny lipid nanoparticles, which are tiny fatty blobs that act like a delivery vehicle for K-ABE to get from the IV through the body and to the liver. Another crucial step was to engineer mouse models for testing purposes, a task that began immediately after KJ's diagnosis. Just like the treatment, they had to be customized to KJ. They took the same sequences they had used to create the custom cell lines and inserted them into mouse embryos. By KJ's 3rd month, the patient-specific mice were also ready to go. Despite his strict regimen and careful care, KJ was experiencing episodes of high ammonia, each one taking a toll on his little body and increasing the risk of irreversible neurological damage or death. I know how this story ends, and yet it is still stressing me out. But you will have to wait a little longer, because we do need money to make the episodes, so it is time for a short break.
This SciShow video is supported by Brilliant, an interactive online learning platform. Brilliant's app can help you gain real knowledge in data, programming, and rings. Basically, learn with Brilliant puzzles fixed like a technological layer. You can start /SciShow, the QR code on screen, or the link in the video description. You'll also get 20% off an annual premium subscription.
In month 4, it was time to meet with the FDA before applying for what's called an investigational new drug application. This is how researchers get approval to administer a new drug to a patient even outside of a clinical trial. In KJ's case, the researchers requested an expanded version of this permission, which is sometimes known as compassionate use. This meeting was when the researchers began getting the initial paperwork squared away. By month 5, the urgency had intensified even more. At this point, baby KJ was even sicker and officially added to the liver transplant list. But finally, in months 5 and 6, it was time to test the full treatment. One possible issue with gene editing is the potential for unintended germline edits, meaning edits that change the reproductive cells and would be passed down to KJ's theoretical offspring. There's also the potential for off-target mutations that might affect the function of any given gene, including mutations that could contribute to developing cancer. So the team did what they could to satisfy themselves that the risks of both of those things were acceptably low. Now, it wasn't zero, but when a life is on the line, a small amount of risk can be okay. They also did a toxicology study in non-human primates and in the mice that they had engineered. Neither the monkeys nor the mice showed signs of toxic effects, which led the scientists to conclude that there was a high enough chance that it wouldn't be toxic to KJ either. The team immediately submitted their expanded investigational application, and the FDA moved fast, knowing what was at stake. 1 week later, the researchers had their approval in hand. It was now the moment of truth. KJ's parents knew that the potential benefits of K-ABE outweighed the risks given his dire prognosis. They gave the scientists the green light. To prepare for treatment, KJ first received immunosuppressive drugs to prevent antibodies from forming against K-ABE. Then he got an initial low dose to check for side effects. And great news, his body handled that first dose without any major hiccups. Soon, KJ was doing better to the point that he could eat more protein without triggering dangerous ammonia levels. He got 2 more infusions at months 8 and 9 and showed even more improvement. K-ABE isn't a cure for CPS1 deficiency. It's a treatment that seems to have greatly reduced the ammonia buildup in KJ's blood. He's not totally out of the woods and will require long-term monitoring, continued medication, and possibly additional doses of K-ABE. It was also too risky to biopsy his liver and sequence the DNA in the cells to conclusively confirm that the intended gene editing had occurred. But the improvement in his condition is pretty darn clear. Something good definitely happened. Which means that after his whole young life in a hospital, KJ got to go home. And we love that for him. Even more good news is that K-ABE's success shows that in vivo gene editing could be deployed to treat practically any genetic disease, like other liver disorders, blood disorders, and even cancers. The personalization is a game changer for rare diseases. Rare diseases have long been neglected because common diseases are prioritized for funding, so that makes this leap even more remarkable. Each type of super rare disease can be as rare as getting struck by lightning, but together, rare diseases diseases affect millions of people. Now, there are challenges to scaling the KABE approach, including designing gene editors that can successfully edit the cells of different tissue types like bone marrow, T cells, and the brain. But KABE has been no small feat for humankind. We've been to the moon, we have developed antibiotics and vaccines, and now we've made life-saving edits in a living child to his literal genetic blueprint. There's this famous sentence at the end of the paper where Watson and Crick describe the structure of DNA. They say that it has, quote, not escaped our notice that the structure they describe implies a way for DNA to copy itself, meaning they knew exactly how significant this was going to be. And the paper describing KABE has something similar at the end. The authors say, quote, although KABE was developed under emergency conditions for a devastating neonatal onset metabolic disorder, we anticipate that rapid deployment of patient-specific gene editing therapies will become routine for many genetic diseases. It definitely has not escaped my notice that there could be many, many more lucky KJs in the future, and I cannot wait to see it.
Crazy, right? I mean, it's really cool, but my God, is it crazy. So cool. And it's really cool to see, like, it actually being applied, and you hear a real life situation that it was actually applicable. Those parents allowed them to use KABE on their baby. Must have been such a hard decision. So one thing that is absolutely crazy, but it's also one of those things that you do encounter a lot within clinical research. So like the type of world that I'm in, we have compassion use cases. And the thing about compassion use cases is that this is it. You get this, or there could be nothing else. And you sort of get to, in a sense, jump the line, and you get to get into the clinical trial or something that it is that you're participating in. I've had compassion use cases where somebody got a heart valve, and it was because it was it was a clinical trial for the valve, and this was the one thing that, like, nothing else would work. And so this is going to be their chance to either get better, or they're, just ultimately not great results, right? When you have no options, you take any option, and you're essentially in those situations where you can get desperate. And I bet it was probably an insane decision to make for his parents, but also, like, I'm so happy that they did, because, like, it's amazing what it's done for KJ, and I'm excited to see what this has to offer for many people in the future. Your baby is dying, you won't be able to live like this. We have an option, but it's experimental, but it's really our only option. It's not that hard of a choice. See, I think that's the hard thing. It's like, this is what you get, and this is how these are your options. But that is roughly the end of my presentation. I wanted to just take a step back really quick and just look at it at the big picture. Genetics really does help us understand how life works. DNA carries those instructions. Genes are the individual instructions, and traits are the outcomes and what we can actually see. Mutations show us that DNA isn't fixed. It can change, sometimes in very surprising ways. Then comes genome editing, the ability to intentionally change DNA. And I think that this opens up a really big door, and as you guys know, it's a huge step forward because it allows scientists to fix problems, study genes more closely, and even develop new treatments for diseases. And tools like CRISPR, like we mentioned, make this possible. CRISPR is very precise, fast, and relatively easy to use, quote unquote. Which is why it has, revolutionized research. But it's very important to remember that it's very powerful. And with that power comes, responsibility, as we all know. Ethical questions, safety, and long-term consequences are all part of that conversation. And the crazy and exciting part is that we've barely scratched the surface, and the research being done today could change medicine and agriculture and even how we understand itself in the coming decades. So, the big takeaway, genetics is, gives us the story of life as it is, but genome editing and CRISPR gives us the ability to write new chapters. But I don't know. I think it's a very interesting topic, and I would love, I don't know. At one point I was like, oh, I'd love to get into CRISPR, but it's insane. It is very, very crazy of a field. Donated her husband and body to science to study rare eye condition. Yeah, it's hard. It's honestly really hard. Decide where your body goes. No, unfortunately you don't. It's rough. Genetics is hard but profitable. Yeah. The other thing I will note for before we take our break is it's rough because there's so many areas of research just in science in general that are so underfunded. And for example, mycology is a really big area that is extremely underfunded, and it needs more traction, more attention, and more money. And it's like, if it's not the hottest, biggest new thing, then it doesn't get a lot of money going to it, especially for like diseases that of course aren't as predominant in life as, like, for example, KJ's case. Not, quote unquote, not a lot of people in the grand scheme of things and like the whole world, how many people we have the disease, but 1 million people is a lot of people. Like, it's insane to think about, but like at the end of the day, it's like, oh, well, for somebody who has like, who's funding research, they're like, oh, well, not that many people have it on the grand scheme of things. But again, it's like, these are people. Everybody has things that they're dealing with, and we need to take care of it, and there needs to be research done about it. It sucks when people don't get the care that they need, or the research that's being done to take care of people. 4 other people in America had gone through when I was 18. It was really weird to go through something that was so under-researched, but it changed my life. Research are being done to figure out my disease. It sucks. It really sucks when things are so super underfunded. And I didn't do it last year, but the year before, I ended up doing a charity stream for a lesser known disease. And I remember raising money for it and actually talking about the science behind it, because not a lot of people get it. But again, it's just, it needs to be talked about. And maybe when people start raising questions or start creating traction about these diseases, maybe we can start putting money into them and people can start, I don't know, just talking about it at least. And then it creates traction, and then we can get money to fund those things. You know what I'm saying? 1% doesn't seem like a lot, but 1% of the entire population is 80 million people. And that's the sad reality of it, is that there's a lot of different areas of research that are severely underfunded, and it's because only that 1% have it. But again, 1% is a lot of people. So I am going to go to a BRB screen so that I can give you guys a little bit of a break. Everybody can go and, do like their little bathroom breaks and stuff. But, before we like officially wrap up, I think I just wanted to just say thank you guys so much for taking the time to just like listen to me yap at you guys for like, what, 3.5 hours almost. And, listen to me give this like crash course mini lecture. I just really appreciate you guys giving me your attention and, curiosity and willingness to learn and engage with the topic. And it means a lot to me. So, even if the topic could be potentially, like kind of a little bit jarring and a little too much at first. I just wanted to give you guys like a sort of a clear foundation of what CRISPR and genome editing had to offer. It's not, of course, like I mentioned, barely scratches the surface of what this whole genre, this whole topic has to offer, but I hoped that it was engaging enough where you guys enjoyed it. But I am going to go to a BRB screen so that you guys can take a little break. And then when we get back, we're going to do a Kahoot. And the winner will get a little prize. So I hope that you guys stick around, okay? Thank you for teaching us about this awesome science. I know you put a lot of work into this, so thank you, thank you. I did stay up really late working on it. I do the thing where I procrastinate quite a bit, just because I had a lot of different things going on, but I am very happy that I was able to put it together, and I hope that I did it somewhat justice. I do better under pressure, unfortunately. So I'm gonna go to a BRB screen. I will be back. I want to say let's try to be back in probably like 5 minutes. Maybe like 3 minutes. Wait, would you rather do 5? We can say like, I can do like 5 minutes. So 4 minutes? Okay, so at like 24. So right now it's 8:19 for me. So at 8:24. All right. Okay. I'm going to do that and then I'm going to get things set up for Kahoot. Okay. So I will be right back. Okay. And then as you guys are still trickling in, I'll start getting things set up, but we won't start. All right. Like, even if I'm back, I'm not going to start like immediately. So don't worry about it. It'll probably be like 8:25-ish when I get started, but just sit tight. I'm going to watch you guys do some, like, have you guys do some BRB random clips. I might come back and just start yapping for a little bit. So just hang tight. Okay. All right. Little kiss. Mwah. You've used both your vents?
No, I still got one.
Okay, I have one.
Yeah, I'm still good.
I was gonna say, dude, we're screwed.
I saw you guys were gonna do like the zip line play, and I was like, damn, that's actually a pretty good play. But
She went up the zip line. I know she did.
Oh, fuck, yeah, no.
I think that's exactly where she went. This map is big. It's a lot of places to hide, so I think she's having a rough time. Oh, Jesus Christ!
Damn it! Ah, fuck! Shit!
Not you using your vent!
Fucking hell! Emma, they're down here! Go get them! That was
Oh God! Oh, that was perfect.
Did I tell you guys I jump scare easily? I gotta get out.
We gotta go.
God, that was so.
Are you gonna really take that Nightmare Maiden? Shiozone? I just took all those effing cards. I just took all those effing cards, dude. I was at Uno? I'm gonna crash out! And I just started. Oh, no, man. No, it's fine. It's fine. No! Is it gonna send us all the way back? It's not, is it? No. God dang it.
Why does it keep doing that?
I have no idea. What the fudge? I don't know.
Alright, dogs are coming out, dude. I'm sweating.
Oh, fudge! She's right there. Oh, fudge. Wait. Ah! Gotcha, ho. What do I do with her? Mercy.
Finger Taker is back, and he wants revenge.
No! You got finger blasted! You can't take my fingies! Just own up to it! Ah! What the fuck? Ah! I'm messing up! I accidentally tapped out. Ah! my little fingies, man. Suck my thumb. You hear that? Did you open that?
Oh no, close that. Close that. Close that. Close that.
Wait, close it. Fabry, hello. How are you? Huh?
Guys.
Whoa! Whoa! Oh, you guys!
Guys, we have a friend.
Get him out of here! Love my makeup. Thank you so much. We gotta take stuff to the cart, though. Can you? What? Are you trying to make money? Get out! Get out! Don't you oops me. Blue, red. There we go. Not the music starting immediately. Let's get back. Oh! 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 Oh!
Stop the, oh, she's doing donuts. Her body
Rip.
just keeps going.
Rip. Stop! You're gonna make me so happy. I'm going to explode. My apologies. I got a little wasted on Friday, and yeah, last night I played Party Animals, like killed my voice, absolutely shot. And today I'm just like, I have this little little throat goat, you know? Not throat goat. It's like a throat phlegm. There you go. Left. Are you scared of the boiler room? Don't be silly. I actually love boiler rooms. Just come with me, okay? Okay, Jasper, let's go. Is he gonna murder me? What's happening? Okay, we're in. I don't see what's causing the noise. Wait, did you hear that? Show yourself. An old man? Oh. Hi. Okay, I was setting up Kahoot and it should be ready to go. Okay, I'm gonna post in the chat how to enter. And I'm going to the screen so we can get in, okay? So basically, if you'd like to join, you need to head to kahoot.it on your PC, or you can use your phone. I recommend just using your phone. I think it's easier. And scan the QR code. Oh, nice. It actually, oh my God, it's letting you guys use your names. Hello, thank God. Hello, thank God. Because it was telling me that I wouldn't be able to. So as long as you guys are putting in like something where I know your username, perfect. Chef's kiss. Love that for us. Okay. And also you can edit the way your little guy looks, by the way, which is really cool. Nah, that can be anyone. I was worried. God, not the Cuckboy67. If you're gonna mess around with your names, you're not gonna be entered into the thing, by the way. I have to be able to know who you are. But if you are using some sort of alias, then you need to put it in the chat. Okay? All right? And then, of course, you know how it is. It is what it is. We know who Cuckboy is. Just for principle of alone, we're not putting Cuckboy in the raffle. in the running. But you can actually edit your little guy to change the way they look, which is really cute. I'm actually really happy that it allows you to change your name, by the way. I'm so happy that it lets you put your name, your username. So happy about that. Okay. If anybody else would like to join, please, like, do now, forever hold your peanuts. I'm Brain Santa. I really like the look of these. I'm actually really surprised of like how you can do these. Hold my peanuts. Hold them. There you go. And if anybody else would like to join, please do so. Basically, I guess there's like a game pin. I've never done it that way. I've only ever done like the QR code, but it is what it is. Okay. I'm gonna put it in the Discord really quick. Just to announce that we're gonna be doing it right now. We are doing the Kahoot quiz now. Okay. There we go. Woo! I'm trying to figure out how to do a genetically superior avatar. I personally don't even get a thing. Mine's just like, oops, all whatever this is. Oh, I think that's like from when I was trying it out. It was giving me like random ones for whatever reason. Couldn't figure it out. But it is what it is. Dude, you don't know how much I love Kahoot. The name change though, right? The name change. If Sun wins, it's rigged. Also, I believe what can happen is if you're tabbing in and out, it'll take you out. And I think you're still technically okay, but I need you in. I think when we start. I'm unsure if it affects how things happen later. If that makes sense. Oh, there's Teague. Okay. Sun knows his music, so that doesn't surprise me. No, Sun is really good at music, and I don't know why. Like, it's insane how good this man is at music. I think we lost somebody, but I don't know who we lost. Oh, I think it was Emmer. I think we lost Emmer. Okay. There's Emmer. Okay. He also just types really fast. He also types insanely fast, which is crazy to me. Wasn't expecting that. Emma left because she's cooked. That's crazy. Here, that's wild. Okay. All right. I'm gonna give it until... I'll give it till like 32. Or maybe like 33, maybe 35. What do we think? Maybe like leave like 5 minutes to get in? I don't know. We'll see. I don't know, man. Them fingies go crazy. Is that so? What them fingies do? I kind of want to go get food after this. All right, I'll give you guys until 8:35 my time, which is in 5 minutes. I didn't take a single note. Nah, I know for a fact I'm getting 0 points on this. No. I honestly think that some questions are a little bit harder than others, but I definitely put in questions that are easier, I think. If you were just paying attention, I think that you would be able to get it. We'll just all go out to dinner after this, okay? Gets more than 60%, he's cheating. I think science does not stick for me. I think it'll be okay. I didn't make them like super hard. It's also, you know, I think it's fairly basic. Like this is just basic CRISPR and genome stuff, so I think we'll be okay. I'm just here for the Kahoot music. Honestly, same. That's how I feel. And dabbling in science articles. More like I remember stuff from my college degree. Yeah, actually, if you guys didn't know, Teague has a degree in biomedical science. I believe in all of you. I think you guys are all do really good. My brain is firing all the cylinders. I think you guys are gonna do great. Pretty much all of my degree knowledge is out of date. I'm gonna be honest, I think that even though I have a background in micro, I still feel like there's so much that I don't remember. Like I have to go in there and like mess around and find out and remember stuff, because there's no way. There's ain't no way. Also, if anybody just wants to like participate just for the hee ha-has and doesn't actually want to like win anything and doesn't want to be known, you can just put it in like a joke thing and you'll get what you need to get. You'll just play to play. You can join anonymously and not have to feel like you have to, you know, What are we gonna eat? Mama Spooky, I don't know. Mama Spooky's like, let's go eat. Let's do it. What are we gonna eat? I don't know, man. I haven't decided that far, but I'm ready to go. It's so cute. Mama Spooky sent me a photo while I was watching a video. Mama Spooky, so she sent me a video, like a picture of my little cousin watching the stream, and she's sitting there and she's taking notes of the stream, which I think is so cute. Ooh, pizza and wings sounds good. Are they not gonna join? I think she would be really cute if she played. I think she could do well. I don't know if they're still here watching, but they could like join in. I think burger and wings would be good. I know we lost a person. I don't know who we lost. We lost somebody. It is an 18+ stream, but it's a science stream, so I make exceptions today. We lost M. God dang it. We're losing people. There she is. Hi, Papa Spooky. Papa Spooky, get in here. We'll see how well you did if you paid attention in class. We'll see how you do. Okay. Did everybody take their notes? Everybody look back? My phone went into EP mode. The EP modes, man. The EP modes. Alright. We are basically done. Alright, I'm gonna start unless somebody else wants to join. Let me know now or forever hold your peanuts. We are gonna get started. I was playing Battlefield. Yeah, Papa Spooky wasn't paying attention to the stream at all. You do you want in here to try to win? Even though you weren't in? We're so brain retained. The notes were my brain retained it. Writing helps me remember what I heard. That's valid. That is fair. If you're just playing Battlefields and you're not planning on getting in, then I'm just gonna go. I'm gonna send it. I'm gonna lock it. Or not lock it. I'm just gonna start it. All right. We're gonna go. All right, you ready? You guys got your phones? You guys ready to go? Or your whatever you're on? I'm gonna start it now, okay? Give you a little kiss. And thank God I didn't start it yet. Sasaku, welcome in! Welcome in, Raiders! Oh my gosh. Hello? Hello, welcome! We're just doing a science stream and we are about to start the quiz portion of the science stream. So that's fun if anybody would like to hang out or join. And I don't know how you guys would be able to answer the questions, but that's okay. Also, Crit, welcome in! Thank you for the raid as well! Hello! I'm so sorry. My stuff is turned off right now, specifically because of the science stream, and I didn't want it to be interrupting at all. But thank you guys so much for trusting me with your guys' communities. Thank you, thank you. Those of you just popping in that don't know me, my name is Miss Spooky, also known as Spooky. I do Cozy Games Mondays, Horror Games Wednesdays, and Fridays are multiplayer days. And we are doing a science stream where we're talking about CRISPR and genome editing. Those of you that don't know, I have a background in microbiology with a minor in chemistry, and sometimes I do science streams where we talk about fun little things. Typically I've done like science analysis of like The Last of Us, or it was World War Z, and I did like a Mythbusters, and I did like a charity stream at one point where I talked about a lesser known disease and talked about the science behind it. So today we were talking about CRISPR and genome editing, and it was really cool. But that being said, thank you guys so much. We're about to get started with the Kahoot question portion. If any of you guys want to try, that's perfectly fine. You could definitely try to win. I'm not perfectly cool. You guys can try to get in on this. I do not. It's open. It's open lobby so that anybody can join in. You can, if you win, you can potentially win a little prize. And the way that Kahoot works is the faster you answer and accurate, right? The higher on the leaderboard you are. So be warned, they've been studying for 3 hours though. But thank you guys so much for coming in with the raid. Thank you for trusting me with your guys' communities. So I feel like all good. Thank you so much for being here. We're just gonna wrap it up with a little quiz and then we'll have some fun. But thank you so much. Tomo, thank you for coming in with the rain. Sezaku, welcome. Thank you so much. Rhea, thank you so much for coming in. Thank you for joining for the Kahoot too. Karma, hello, welcome in. Misty, welcome in. I just want to make sure I say hello to everybody. And Crit, thank you so much for the raid as well. Lord, hello, welcome in with the raid. I really do appreciate it. Nitrous, hello, welcome in. So I can devour some chicken nuggets, as you should. Get that food. As you should. Get that ASS. Anybody just coming in with the raid, get that ASS as you need to, okay? All right, I'm gonna go ahead and start it now, okay? Should we wait for ads? Oh, yeah. Can we snooze this? Is that snoozed? I think I snoozed it. I think we're good. I don't think we're in ads. We only had one snooze left. It said one of... I don't know about that because it told me I had 2 of 3 left. All right, I'm gonna go ahead and start it. It's 20 questions. I don't think it should take us that long, okay? All right, I love you lots. Mwah. I believe in you. You guys got this. All right, have fun eating your sourdough. Let's get started. It'll show up on your phone and on stream. True or false? RNA stores genetic info long term. I'm gonna turn off my camera for this. What is up with this music? This is not the music that used to be there. False. It is indeed false. RNA stores genetic information short term. Okay. You guys ready for this? RNA stores genetic information short term, not long term. DNA stores genetic information long term, okay? All right. Next question. Oh. This is the leaderboard as we speak. There we go. Q is in the lead. What is Cas9? I don't know what's up with the music. The music doesn't typically do this. I might have to try to like play with that here in a second. Look at everybody. A protein that cuts DNA at a specific location. That is exactly it. It is not a virus or a sugar molecule or a type of RNA. So, let me see if I can get my music up. No, I guess that's it. I guess I can't change it. Bummer. The setting isn't available for ongoing Kahoots. Love that for me. I can't change it. All right, well, next question. Ready? Let's see. Q is still in the lead. And then we got Nia, followed by Comedy, then Teague, then Sun. All right, it's a Punnett square question. Brown eyes. Big B are dominant over little b blue. %. So I'm gonna pull up really quick what this looks like. Okay, hold on. I'm gonna show you guys really fast on stream why it is 50%. Okay, I'm gonna show you really quick. Give me one moment. I have a slide where we talked about it. Okay, so we're saying big B and then little b. So one parent has big B and a little b, and then a little b, okay? And then if you remember here, this is the Punnett square. So big B, and then little b. And the chances that the child would have blue eyes would end up being 50%. I'm answering as fast as I can. Q's faster. But yeah, little b. So there's a 50% chance that the child would have blue eyes. I told y'all there would be a slick little Punnett square question in there. All right. Ready? Let's see the leaderboard. Ooh, Q is still in the lead. Comedy is now in second, and then Teague is now in third. And apparently Teague has the highest answer streak of 3. All right, y'all ready? But I don't know why it says that. Traits are blank. Correct. Observable characteristics influenced by genes and sometimes environment. So, like I mentioned, it's determined by your genes, but a lot of the time it can be determined by the environment as well. The example that I provided was, let's say, for example, you have strong muscles, right? Or like a gene for strong muscles. Well, if you don't nourish or work out those muscles, you're not going to have strong muscles. Or if you have a gene that's predisposed for you to have, genes to have like height, really tall. If, during childhood, you were malnourished, then you wouldn't really be able to reach the height, your full potential of height that, that your genes are coded for, right? My genes make me prone to be a nap taker. Valid. Okay, I do see that there is going to be an ad, so I will do the next one, and then we'll stop and do a little mini break, and I'll talk a little bit, and then we'll go back in, okay? All right. It looks like Q is still in the lead. Okay, so now it says Comedies has the streak of 4 correct answers now. Q is still in the lead, followed by Comedy, Teague, Nia, and then Sun. All right. DNA is shaped like a... Oh, this is the music I know. A double helix. I was really hoping that one of you guys would maybe fall for my other ones. Spiral helix was a dirty trick. I definitely put it in there as like a as a tricky one. I was trying. I did my gosh darndest. Okay. We'll look at the leaderboard. And then I won't move on to the next one yet because it looks like we're in a lab. Does a triple helix exist? Ooh. Yes, technically, but it's rare. And it's not a standard form of DNA. It can be seen in mostly in lab conditions or very specific cellular context. So collagen, yeah, but in the sense of DNA. I think your doorbell is ringing. Go check so we can do a question. I just thought it was a cool sci-fi thing from Assassin's Creed. Cool, thank you. But triple helix DNA is real, but not the normal structure of like DNA cells. The double helix is what's standard. But research, it's been researched like in labs mostly. I'm only 43 points behind. I can come back. I just gotta be on it. So close, honestly. Okay, it looks like the ad break ends in like 50 seconds. Does anybody else have any questions or anything? I hope you guys are liking the little Kahoot. I try to throw in some like easier ones, but I also try to throw in some ones that were like a little bit... I don't have any ads. I don't know if anybody else... Because it tells me that we're in like 30 seconds into an ad. I'm 908 behind Teague. Need to lock in. Apparently there's a triple helix piercing. That's kind of cool. There's a triple helix piercing. What does that look like? Hold on, I'm looking that up. Triple helix piercing. What does that look like? Oh. What? Like that? Oh, interesting. Triple helix DNA, by the way, looks insane. If you guys didn't know what triple helix DNA looks like, it's basically spaghetti noodles wrapped around one another. Okay. I think we are back from the ads. I think we're good to go. Are y'all ready? We're gonna move on to the next one, okay? All right, I'm starting it. Which is a DNA nucleotide? Adenine. You are correct! Adenine. Ugh. Oh god, I panicked. Alright, let's see. Hey, yo. Hey, yo. It looks like M. M is now on the leaderboard. Looks like we got it. Okay, so now we have Q, followed by Comedy, then Teague, then M, then Nia. Man. Alright, are we ready? Moving on to the next one. Which molecule guides CRISPR to the correct spot in DNA? Also, what the fudge is up with my song? Wow. Love that for us. They said, no, you don't get music this round. Sorry. I meant to click the other one. It was indeed RNA. RNA is what guides the CRISPR. I was so slow. I was looking for the word guide. So it's RNA that guides the CRISPR to the correct spot. And it's not protein Cas9. Remember, protein Cas9 is the tool for snipping. Oh my gosh. Comedy is now in first. Then we have Q, then Teague, then M, then Sun. I clicked ribosome on accident. All right, you got ready? Next one. Oh, it's not even gonna give me my music. I'm just gonna make Kahoot music in the background. Oh wait, it is doing my music. I'm sorry. My phone just got disconnected. There we go. We're good. Okay, look. Which base pairs are correct in DNA? A pairs with T. C pairs with G. T does not pair with G. G does not pair with A. And A does not pair with C. How did you memorize it? How did... A and T and GameCube? I love that. Hey, honestly, I'm a big fan of people like making little things, little sayings. A titty. Cool guy. Okay. All right. We have two different types of people. All right. Let's see how we look. Comedy is still in first, then Q, Teague, M, and then Sun. We are in question 9 now. Ready? Let's go. Which of the following is true about genes and chromosomes? Yes. Genes are bundled into chromosomes. Humans inherit not 2 copies of every chromosome from one parent, but 1 copy. And genes are bundled into chromosomes. They are not larger than chromosomes. And I didn't even answer, apparently. I thought it said chromosomes were bundled in genes. And I was like, that's wrong. All right, let's see. Ooh! Ooh! Q is back in the lead. Then followed by Comedy, then Sun, then Teague, then Nia. Crazy work, princess. Are y'all ready? We're going. Genes code for proteins. Genes code for proteins, not phosphates, fats, or nucleotides. They code for the proteins, y'all. All right. Q is still in the lead, followed by Comedy, Sun, Nia, then M. Y'all ready? This is question number 11. How many chromosomes do humans have? Humans have 46 chromosomes. Now, I know why a lot of you chose 23, but there are 23 pairs. It is pairs. They're not... There's 46, but 23 pairs. So... throwing that out there. All right, let's see. Thought a chromosome was a pair already for a second. Nothing. I think I'm gonna flunk out of this class. That's so tricky. It was a trick question. It was. It was. Q is still in the lead, followed by Comedy, Sun, Nia, then Teague. I had a feeling I was gonna trip up some people with that one. A chromosome is... They are, so each individual, those are the 46, and then together that is the pair. So, hold up, wait a minute, give me a second. Right here, so you have 23 pairs of chromosomes in each of their cells, and there's 46 DNA molecules, and these are the chromosomes. All right, are we ready? Let's go. Where are chromosomes found? Nucleus. Look at you guys. As you saw here, you guys did it. So Chromosomes are found in the nucleus, the control center, and I just showed you the slide, so it was a little extra help. But also for that last one, humans have a total of 46 DNA molecules. These are organized into long coiled up structures called chromosomes. So it was labeled a little bit funky, but apologies if that was a... But there it's like written as you have... These are organized. They're called chromosomes. So the 46 DNA molecules are chromosomes. Ready? Let's see where we are. Q is still in the lead, then Comedy, then Nia, Sun, and then Teague. You ready? I knew I was gonna trip up some people's. CRISPR was adapted from... You are correct. It derives from bacteria. And it does not derive from plants, animals, or viruses. It's from a bacteria's immune defense mechanism. Zoned out on this part because those videos are my sleepy time videos usually. I did talk about it during the lecture though. Bacterial immunology thing. Yeah, you got it. You got it. All right. Q, still in the lead. Then Comedy, then Sun, Teague, then Nia. All right, you ready? Question 14. Punnett squares help predict... And you guys are right. Trait inheritance. No questions asked. Y'all got it. Looks like no movement on the leaderboard. Everybody stayed the same. Getting closer to touching you, son. Get out. All right. Question number 15. What can CRISPR do that older gene editing methods struggle with? Correct. It targets specific genes. It doesn't cut RNA. It specifically, so it uses the RNA to help transfer. You know, so basically they're like the complex. The CRISPR complex is when it's with the RNA and the Cas9. And that is what the RNA is what's helping guide the Cas9 to where it needs to go. And so that's where we're going. That's where we're going. All right. Okay. Looks like no change on the leaderboard. Someone get cut Q's internet. All right, ready? Let's go. CRISPR is used for... It is used for DNA modification. Not specifically for repairing broken chromosomes or copying DNA or predicting genetic traits. It's for genome editing. Okay. Let's see. So, looks like I think that we stayed all in the same spots for the scoreboard. Okay? All right? This is going to be question 17. And that's like, what, 3 more? Not too many left. We're almost there. We only have 20 questions. I just like it's based on speed. Yeah. The unfortunate part is that this is how it worked in school. And like, it's the only way that I can determine like real life, like real-time quizzes. It's unfortunate. All right, you ready? Let's go. Double points. Which is a CRISPR step? It is cutting DNA. Cutting DNA is a CRISPR step. Painting, freezing, and heating are not CRISPR steps. Kind of gave it away with the picture. It was a little bit of a give me, but I tried. All right, guys. No movement. Everything has stayed the same with the leaderboard. We are in question 18 now. The Human Genome Project has determined that humans have an estimated blank genes. Correct. Human Genome Project has determined that humans have an estimated 30,000 number of genes. Crazy. And we have Q, Comedy, Sun, Tegan, Nia. I think that's been the leaderboard? I think. I don't think anything's changed. All right. Are we ready? This is 19. Only 2 questions left. All right. Let's go. What does CRISPR stand for? You're looking for a specific word. It is clustered, regularly interspaced, short palindromic repeats. That is exactly what CRISPR stands for. Hi, chickies. Chickies, you're at the end of the lecture. They're doing their Kahoot to see who wins. This is actually the last question. They're gonna see. They're gonna do it. All right, let's see who's on the top of the leaderboard right now. Okay, so Q is still in the lead. Then we have Comedy, Sun, Teague, then Nia. Queen! You're gonna win the Kahoot right now? Okay, we're on the last question. Y'all ready for it? All right. Okay. All right. Doing it now. Which is a type of mutation? There we go. Substitution. If you guys remember from the lecture, types of mutations. We had substitution, insertion, and deletion. Those were the types of mutations. I'm not surprised that Q1, he had a professor who worked on CRISPR. Yep. And this is it. In third place is Sun. In second is Comedy. And in first, we had Q. Then runners up were Teague and Nia. Congratulations. All right. I hope you guys liked it. I had a good time. I had fun. Yippee! We did it, y'all. We effing did it. Let's go. Ho, ho, ho. Okay. All right. That was the end of the science stream, guys. Q, do you have whispers open by chance? I hope you do. How many did I get right for not watching? Hold on. I might be able to tell. Not my dad being like, how many did I get right, even though I didn't care to watch. Okay. Okay, you have whispers open? Okay. Stay tuned. I or my mod will be reaching out to you via whispers just to send you it's gonna be a little Steam gift card, okay? Little gift card code. So just throwing that out there. It's gonna be a little surprise. So a little prize. And yeah, hold on. I'm trying to look at my thing to if I could see the report. Let's see. I'm gonna look at it. Options? Can I see? Yeah, reports. I can look at reports on here and then I can look at it. Let us see. Let's see what Papa got. Papa, you got... Do you want me to tell you? You got 55% correct. So you got... I can actually see how many people got correct versus how many people got incorrect. And I can see how fast they did. Mama was watching and she had more answers wrong than me. You failed, Papa. I was in last for like 4 rounds at the start there. No, you're okay, Emma. You're okay. How many did I get correct? Emma, you got 55% correct. Yeah, it says you got 55% correct. And I don't think anybody got a full 100%. I don't think anybody got a full 100%, but we did get like really close with like 95%. Son, you actually got 90%. Okay. Let's go decide to raid out. Thank you guys so much for being here. I had such a fun time. It was such a good time. Okay. All right. Who should we raid out to? I had a really, really fun time. I hope you guys enjoyed the stream. I always have a blast when I do science streams, and truthfully, so much fun. So much fun. Okay. What is your friend doing? If you don't mind me asking. Okay, they're playing Strange Techniques. Sure, I'll raid out to them. Yeah. Okay. It looks like a really cool game. So let's raid out to them. I'm gonna search. And their name is Toto Kitty. So we're gonna go ahead and start the raid. Hi, nerd. Welcome in. We're about to raid out, but thank you guys so much for joining me today. Thank you for being here. I really had a wonderful day. Wonderful time being with you guys. Give me a second. I'm like, I know that the raid message isn't going to work if I don't turn on my bot real quick. I turned off all redeems and everything, just because it was a little crazy. But thank you guys so much. We will be live again on Monday. We're going to be playing some more Dragon Age Veilguard. We're also going to be doing Alien Isolation next Wednesday. We're going to be starting Shift Happens next Friday with Sun. And then, there it is.
Holy shit, it's Pajama Sun.
There's the raid message.
So much aura.
It's gonna give all the walk-ons right now because I'm turning on the bot for the raid message.
I fear the swag is too hard.
crazy. Anyway, thank you guys so much for being here. Wednesday, we're gonna be playing more Alien Isolation. Friday, we're gonna be playing Shift Happens with Pajama Sun. And then Saturday, we're actually gonna have our co-op stream with Papa Spooky. So hopefully you guys can make it. We're gonna be playing We Were Here Too. So have a wonderful night. Thank you guys so much for playing and hanging out and listening. Peace out, ghosts and ghouls. Good night and bye-bye.